Summary. Okay, let me just. I had to ended up leaving for it. So I will. And I think also I was supposed to send this. I did send this. Okay, review of day 1 and day 2. And then, so we can look at this. All right, so where are we so far? So where we are right now is we have covered difference and differences. We're on day 4. Welcome to day 4. Sorry. I was up late watching 3 Body Problem on Netflix. Highly recommend. It was so good. Very different, and I'm a little tired. Let's see. But let me get us up to speed here. So what is diff and diff? Comes from the design tradition of causal inference. And you need longitudinal data before and after. You need a unit that's treated, and you need a comparison group. Now, we said you need a comparison group who is not treated. If you use a comparison group who is already treated, you're going to have to make assumptions about their treatment effects. And that's we've kind of touched on it, but we haven't really gone very far in a productive direction. I think in terms of, using already treated groups as controls, we've just said don't do them. Okay. So then we said, all right, what are the assumptions for the standard diff and diff? And there's 3. Without covariates, there's 3. No anticipation. Your baseline outcome is untreated. So y equals y0 at baseline for the treated unit. Sutva, no interference between the units, no variation in the dosages, no variation in dosages when you are defining the treatment as a binary treatment. So make sure there is no interference between the units and the comparison units, that Sutva. That guarantees that the post-treatment control group units outcomes are Y0 also. So here, all right, so this is diff and diff, this is the OLS. There's our coefficient. Y1 post-treatment outcome is a Y1 for the treatment group. No anticipation. Pre-treatment, treatment group, Y0. Sutva, comparison group in the post-treatment remains untreated, even though that one has been treated, Y0, and that's a Y0. Put all those together and what do you get? You get this right here will identify the average treatment on the treated plus parallel trends. The standard, as Saden said, the standard parallel trends assumption is all that you have left. And because you're working with longitudinal data, you can sort of check in the pre-trends whether or not there's evidence that would suggest that the treatment group and the control group appear to be on different paths. Okay. All right. And that's the event study. The event study checks if they're on different paths, and the falsifications check for what we would possibly consider post-treatment differences in the 2 groups. Okay, so the event study sort of tells that the treatment group and control group are trending similarly, and the falsifications say that post-treatment 2 groups are that there doesn't appear to be anything spurious in the post-treatment period driving the results. And that's ways to think about the two roles of the falsification and the event study. Event studies look before, falsifications look after. Okay, so, but sometimes it doesn't hold. And that's where we go into covariates, triple differences. So those are like our 2 ways of thinking about how to handle violations of the parallel trends assumption, which was mainly about comparison groups. That's the way to think about parallel trends. Sutva says no interference, no anticipation says make sure that your baseline is untreated. Parallel trends is really about comparison groups because it's about two different groups being compared to one another, right? It's only one of those assumptions that's making a statement about the comparability of the two groups. We're going to be in this review on GitHub. I didn't put it on GitHub. I thought that I emailed it. Did I not? I thought I emailed it. Oh, I didn't even email it? I thought I did an Eventbrite thing. Well, I need to do an Eventbrite thing. I could have sworn gosh, why did I think that? Oh, maybe I started to. Okay, well then I will get this sent out. I'll get that sent out. And then we'll send it. All right, I'll do that at the 15-minute break. I'll wrap all this up and get it sent. I didn't put it on GitHub though. Because of the because GitHub goes to everybody. All right. So then parallel trends is really about the control group. And so we have some options here about how to handle violations of the parallel trends while still using the same control group. One was covariates. And covariates was allowing you to continue to use the same control group, but to try to find effectively like matches. It was effectively like matches within it. At least it introduces covariates into the analysis, and then you have to build an estimator that accommodates it. And we talked about three. One was an outcome regression approach, which is what we're gonna. Do I recommend it? If you believe that you have a violation of parallel trends, if your pre-trends look pretty bad, then I would say yes to doing some kind of sensitivity analysis. I think that's no one's doing it yet at Ordo. It's not a very commonly done procedure. So if you did it, you would probably have to think pretty carefully about how you're going to write the paper up and how you communicate it in a way. It's obviously true. I'm just saying sometimes people are wanting this diff and diff. They're wanting the diff and diff to become very formalized as to what the steps of procedures are. And all I'm saying is that that the honesty approach that Rambakken and Roth have developed, I would probably study that very closely and think carefully about how you want to incorporate it into the project. But yes, I would say absolutely that I would consider that kind of thing. I don't know if it's not all of the yes, I would. I don't teach it because of the time, but yes. So triple differences, covariates. So with the covariates, you have outcome regressions, and you also have the inverse probability weighting approaches. Is kind of these two approaches. Outcome regression is what we're going to talk about today, as well as more of this 4 averages and 3 subtractions approaches. Okay. Day 3, we looked at, though not covariates, we looked at the anomalies of the two-way fixed effects estimator when you have more than one treatment group, and how two-way fixed effects specifications will just automatically use already treated groups as controls. And when you use already treated groups as control groups, it introduces bias, as we showed, if there is heterogeneous treatment effects. So we talked about that. Primarily within the Andrew Goodman-Bacon paper, we talked also about fixed effects as a class of estimators. We looked at Andrew's decomposition paper, and we looked fairly deep into that. We did a simulation to try to illustrate this practically so that you could see it. And then we looked at a solution. We looked at the 4 average 3 subtraction style solutions And that was the only one we had time to really get into was Callaway and Santana. So what we're going to do today is we're going to finish this up now and look at the event study with Sun and Abraham. We'll briefly just, depending on the time, we'll see how much time we have to just look at this little bit that I've developed for explaining to Chase Martin into Hopeful's negative weighting. But we might, just to save time, go directly into the outcome regressions of Borsak and Gardner. All right, I'm not going to cover Wooldridge, but Borsak and Gardner, because these all sort of begin to be fairly similar to each other. And then we'll review a couple of papers that are modern that use differential timing. Modern, they're not even, one's published, one isn't, to try to kind of give some advice as well as show a little bit about how people are taking all of this information and using it to do the practical part of the studies, which is, you know, what you know, not so that you don't end up going in a direction where you can't see possibly you know, how to just continue to do basic science, do basic stuff with all this, and you get sort of lost with all these new estimators and you sort of forget what it means to be working on your project. So I just kind of wanted to show a couple of papers about how they're doing it so you don't lose sight of the big picture. And then today, we're going to continue to work on, we're going to do Sun and Abraham event studies and outcome regression, and then we'll move into the continuous treatments. And I don't know why I say discuss a new paper, but that's what we'll discuss. I don't know why I say that, but we'll do that. And that'll be it. Okay, that'll be it. So we'll see where we are today. All right. So I wonder why I thought I sent that. I don't know. Oh, here we go. All right. So let me see where we are. So we are going to be here. Page 96 of ATTGT. That's where we're going to be. Page 96. And this is referring to Sun and Abraham. All right. So it's page 96 right here. Aggregating the building blocks is how this is kind of currently framed. And then we'll go Sun and Abraham. It's like the 4 averages, 3 subtractions, but it's focused on the group time, the smaller building blocks and building up. All right. So why are we doing this? Why are we doing this right now? So Callaway, Santana, and Sun and Abraham. All right. Sorry. Andrew Goodman Bacon and Callaway and Santana. Both, as we've discussed it, we're focused on the simple regression specification with a single dummy. All right. So what it was focused on. That is the way that we've taught it. So, you know, Bacon showed that the quote static specification, i.e., a single dummy for treatment with, you know, panel, unit, and time fixed effects, right? He showed that the static specification equaled weighted average ATT terms plus weighted average parallel trends terms minus change in ATT for the earlier treated comparison groups. Okay. So you had this, like that last part. So you had to assume constant treatment effects to justify using the 2A fixed effects specification. Okay. That's why sometimes it'll be called, you know, and we actually saw this. We could just like real quick. We saw this on the first day. when I went back here to this 3 waves, when we did this event study. Event studies really take off. Um, Starting around here, they really rise. They become like the number of papers that say event study and parallel trends just starts to grow. And this is the words parallel trends. This is the word event study plus diff and diff. It starts to grow a lot, but it again really starts to take off. Okay, it's been taking off more and more where you've got papers being written that say diff and diff and event study. And here's an event study. This is the earliest one I can find, an event study that does differential timing. So it's time relative to year of adoption, and everything noticed here is being expressed in terms of relative time, not calendar time. Because when we usually did a diff and diff event study before, if there's only one treatment group, then you would only have, you would do event studies in terms of calendar time. So you would be like, New Jersey passes its minimum wage, Pennsylvania does it, and you would just track New Jersey versus Pennsylvania over time. And you would have in the bottom, you'd have actual years. But David Otter does differential timing in his old 0803 paper on unjust dismissals. And he's got here the year of adoption. Here he's got pre-treatment. Notice some people were like, well, how many years pre-treatment should you have? Well, here Otter only had 2. Okay, so he goes 1, and that's and I don't know how this is possible to have a confidence. I don't know if that's the baseline. A lot of this I don't know. Year of adoption, 1 year prior. I don't know how he estimated this regression. But so you've got here this pre, then you have 2 years pre. Then he's got after. Okay. And here's what he says. In applying the diff and diff framework to the data, it is important to consider carefully the quote experiment created by these court decisions. In the ideal case, court decisions would be independent random events that varied in timing, had no spillover effects to non-adopting states. So there's Sutva, and there's this randomness. He said, ideally it would be random. If it's random, randomization usually solves everything. You might not know exactly how or what terms are getting canceled out, but they will be. And if they're random, if events are random in a diff and diff, then parallel trends will hold, because parallel randomness means that the distribution of the characteristics are the same for the 2 groups. One group getting the events, one group randomly not getting the events, and so parallel trends you could be confident in it. But he just says in the ideal case. And then he says, assuming further that the treatment effect of the common law exceptions was constant. Okay, was constant. So he says already back even in 03, he's aware that, well, he seems to know that you need constant treatment effects. Okay. But what we're going to now look at is, well, what if you don't have constant treatment effects in an event study? Because all that we had here was Andrew Goodman Bacon was analyzing. That's a good question. I'm not positive what I would think about that. I mean, probably it's probably not random. It's definitely not random in the cross section, because it's not randomly, it's never happening in Waco. Because we literally don't have the kinds of plates, issues that you would have in California. So it's not random where it's happening. Might be random when it's happening. I'm not positive exactly how to think about it. Not positive. It's not, but that said, Andrew and Pedro and Brant, they do not analyze the decompositions associated with the event study. Pedro Santana and Brant Calloway's estimator will work for an event study. But my point is, Andrew's paper does not explain what is wrong with the event study. Okay, he does not analyze the event study. He analyzes the single dummy variable specification. He analyzes this. That regression. Is the only thing Andrew focuses on is this regression and that number. And when he does that, he shows that this coefficient is equal to all of that. Okay? But this coefficient, this coefficient is not the event study. It's a single coefficient. It's a single specification. So what we're going to now do is we're going to try to understand how do we think about the two-way fixed effects estimation of the event study leads and lags. Is it fine? And the answer is it's not fine. All right, so how is it that people have historically done event studies? Well, it's interesting. I mean, David Otter in 2003 does a regression-based approach. But for some reason, that doesn't always catch on. So Mark Anderson, Dan Reese, and Ben Hansen did a study on medical marijuana laws, MML. And they wanted to make an event study. And I don't know why they did it this way, why they didn't just do what David Otter did. This paper shows up in 2013, 10 years later, but they don't. They decide what they want to do is illustrate they want to illustrate an event study in their own way by showing the raw data. And so when they do that, here's what they find. Okay. So what they decide to do is create an event study with raw data. So David Otter is using regressions, log points. Okay. He's using regressions. And they want to not go directly. They don't want to show a regression. What they want to show instead is the raw data. But they're going to have this problem. It's easy enough to code up this black line. You can always code up this black line with differential timing. You just do this. Okay, so it's like you've got this time till variable. You've got all of the treated units have this all of the treated units have a time till variable. I created it like this. I generated it as a variable that was called time till year minus treatment date. Okay, year minus treatment date. And all it is the variable year minus the treatment date. So whatever year of the panel it is, minus when that unit is going to get treated is the time till treated. It's a relative time indicator. And if you wanted to just plot the raw data, all you would have to do is just take an average. All you'd have to do is just take an average over all of these variables. So it would be like, it'd be something like this: collapse, mean, L, be like Y by time till. Okay. And then I'd have 48 observations. And all I would be doing would be I'd be looking at the average of the outcome for each relative time period, right? So, but the problem is all that this gives me is the the average outcome for the relative time period for a treated group, right? It's all that gives me. Because all I have is what's the average outcome for anybody's negative 24? What's the average outcome of anybody's negative 9? But you need for these things, you have to put up a quote control group. But a control group doesn't have a like let me show you. So we'll go here to the lab. We'll go to Ching and Hoekstra. Okay, so here's the Ching and Hoekstra paper. This is all the murders. So we say let's do the same thing. Let's say gen time till equal year minus F year. Okay, drop time till. Gen time till, so tab F year. What's F year? This is the dates when everybody was treated, right? Now I've got 550 observations. 231 of them are in a treatment group. That means that the rest, 550, that's 320 or 319 of these observations are untreated. And you can see this, you can type, tab count if F year equal period. I've got 319 state. I can go tab state if F year equal period. So I've got all of these states here never get a law. They never get a law. They never get a law change. And so, I've just got tab state if F year not equal period. These are all the states that do pass the laws. Okay, these are states that do pass the laws, and these are states that don't. If I type in gen time till equal year minus F year, right, I end up with 319 observations that do not have a defined time till variable, and that's because of this list state. Let's set more on list state year treat. No, CDL time till F year if time till not equal period. All right, so here's an example. Alabama. Here's Alabama from 2000 to 2010. In 2000, they're treated in 06. It's 6 years before they're treated. They're treated in 06. 58% of the year they had a law. So Mark and Ching did like a continuous treatment. In the year of the treatment, nobody gets a 0 or a 1. They get a % of the year treated, right? It doesn't really change anything if you change that to a 1, but that's how they do it. So we have here this time till, right? So Alaska, we have a defined time till for Alaska, but you don't have a let's do it like this list if it equals period. Right, well this guy never is treated. Arkansas is never treated, so that's a period. It's missing. So when I type in generate time till equal year minus F year, it's undefined. So how in the world could they ever do this? I could type in collapse mean L homicide by time till. But see, I would only have the average homicides. I would only have the average homicides for the treated groups because they're the only ones that have any values for -9, -5, 0, etc. So how is it even possible to make a picture like this? If I have states that have no laws, then they have no defined years since legalization. So how would they do it? Well, what they did was they did like their own creative, it's like their own creative solution. They randomly assigned to each state one of the treatment dates. They just randomly assigned it. They basically were like, took a randomization of, like resorted the data, and they just, basically picked of the control group randomly treatment dates. And if they just randomly picked treatment dates, then when they did this right here, when they just collapsed and took the average, they'd be taking it for everybody, but they would have had like it would have been like this. They would have had like, by time till treated. And then they would have two. They would have two different, it would look like this. So we'd do it again. Okay. And then it would be like, I can't off the top of my head figure out how I would do it, but they randomly pick, treatment dates, and then they would do this. They did like this. And then they had like two. They had two. They had like, a control group average, and they had a treatment group average. Okay. So they randomly did it. Yeah. That paper I think is primarily about synthetic control, but that's a good example of trying to think about how to describe the um the events as whether or not they're random or not. So this is what they do, So Pablo says, do I recommend it? No, I don't. I think it's like, I think it's fine. No, I don't. I don't recommend it. Because it's just kind of a way of illustrating, and it didn't really matter. It didn't really matter because if you look at this, the thing is the people that aren't treated, their treatment values, I mean their outcomes seem to be pretty stable over like whatever years you're using, but it's kind of like this is sort of nonsensical. None of this really corresponds to anything. So, but you can see why they did it. They basically show, that the treatment group is watching. I mean, the treatment group is watching this decline in alcohol related traffic accidents and sort of falls. And then they want to show essentially an event study that may kind of give the appearance that, they want it to be that you could sort of interpret this as like a treatment effect, but so I did it. I did it too for this like Craigslist paper that I'm working on with Melanie Goldie and Christine Durrance. Craigslist was at one point one of the most popular websites in the world. And it had for a long time, it had a personals section where it said men seeking women, women seeking men, men seeking men, women seeking men. It was like a casual encounters kind of thing. And we used the Wayback Machine. I've done this for a different paper, but we did it again for this paper where we used the Wayback Machine. And this is something you might just look at. There's another paper that we're gonna talk about later, but the Wayback Machine is great because the Wayback Machine lets you look at a history of all the a history of the website. I think I typed it in wrong. Oh, it's .org. Okay. You can go to like here. You can see what the website looked like historically. They take a photograph of it every day. So we went through and you can see here that there was this See, what I did was I used it for a different project that was just published where we looked at the appearance of the erotic services part of Craigslist, and certain cities get their Craigslist at different points in time, and also they update the front page of it at different times. So it's like you look at Houston. See, like Houston, it looks like Houston always had when Houston rolled out, they always had the personal section: women seeking men, women seeking women, men seeking women, men seeking men, missed connections, casual encounters. But their services did not always do the erotic part. If we like jump ahead here to 2012, actually, no, we want to do it a little bit sooner because they take it out, they remove it. All of a sudden there is an erotic services section, but then they eventually take it away. If you look at like 2018, it's not there. And also they also take away the personals. So you can't find the personals on here either. Women seeking women, all that stuff, that goes away too. Misconnections is still there. But I believe that the hookup part, the romance part goes away. Okay. So what we did was we went through for every county in the United States. We went through and we tried to figure out, first we went through every county. We found all of the associated, the nearest Craigslist, and we figured out when it was that county got treated. Okay. We had a bunch of counties that never get a Craigslist anywhere near them, and we had a bunch of counties that did. And so we've got this treatment date, and we put everything in terms of the relative time, the time till variable. And then I randomly assigned to the non-Craigslist counties, randomly assigned a treatment date from the treatment dates that we had. Okay, from the treatment dates that we had. I did this one day. This was a long time ago. And I saw a picture like this. It's not so different, it's kind of similar. And it was the start of the research project because we were finding this surprising result, which was we were finding when we did this picture, we found that the treatment effects looked to be negative. That when a county got treated with a personals section that was basically like Tinder or Grindr, I guess you could say it was probably like a dating part of it, but I think it was it was more for casual encounters. I don't think it was like I don't know if it was, well, it's not clear. I think it got used I think it got used more for the hookup part and less for the permanent thing. Anyway, we found these negative things. We were really surprised. So then I was like, what we need to do though is we need to do this. We need to create yes. It's a fairly strong result too. Why? I'll actually show you in just a second. But I'll show you what originally put the project down. So we were finding a negative effect on birth rates, and which was the opposite of what we went in expecting. We were expecting positive. We were expecting unwanted children kind of thing, and we were finding the exact opposite. And it's a very robust result. But then when we did the event study, we did not. No, we didn't do that. Because usually we're doing these when we do an event study, Reese, it would be lagged because it would be like, what's the effect a year later? What's the effect 2 years later, 3 years later, 4 years later? We would do it like that. It would get lagged, but in the diff and diff, it's just measured as an average treated on the treated. It is progressively rolled out. It is progressively rolled out. It's differential timing. So we're handling it with the differential timing using difference in differences. And what you would hope to do is to be comparing units that are getting treated to units that are not getting treated at that same point in time, that are comparable to each other, that are comparable. And in this example right here, when we do this randomization, these are not the right years. These are not the same years as any of this. And when we do the and so yeah, we'll get to that way. Maybe I'll show you the results. Yeah, yeah. I'll tell you what we don't know. I'll tell you what the hypothesis that we're now interested in is this idea of permanent dating. That the apps, it's not really about apps because it's about the same kind of platforms that allow for more quote unquote more efficient dating markets. We're wondering if it's not contributing to people staying in a dating relationship, because really you have children with someone you're not dating. You're not usually having children with people that you're dating. You're having children with someone that you're planning to stay with in a fairly long period of time, usually, and in a fairly non-dating relationship. It could be marriage, could be cohabiting, but it's usually a long-term relationship and you've exited the dating market. And so what we're wondering is, could this be causing, yeah, we could be finding different things, where it's surprisingly turned into a big project. But what happened though in the history of this project was this picture made us go, what is going on? And we had two-way fixed effects results. We had two-way fixed effects results because this project was started before all this diff and diff stuff. And we had these diff and diff results and from two-way fixed effects, and we found very large negative effects when we did this regression, and I ran that regression, that coefficient was very, very negative. And then when we did this right here, it was looking like, the reason it was really negative was because we were finding this divergence. And it did kind of look like, but it's so noisy at the monthly level. But anyway, I do an event study. So this is the event study, and I'll show you how to do this. Okay. So what is this? You run a regression onto one fixed effect. This would be like the county, month fixed effect. And then you have a dummy for every relative time period. So it would be like this. Let me do it here. Okay. So what you do is, what this here is called is this one here, when it's inside this like bracket, this basically says, all right, here you have these dates, and you're going to dummy out year minus treatment date. Year minus treatment date. So that's here. Year minus treatment date. So when you have a dummy in the event study specification with two-way fixed effects, when you have a dummy, you are going to create a time till variable. All right, you're going to create a time till variable, and you're going to run a regression onto panel fixed effects and time fixed effects, and then dummies for every time till variable. Okay, so how would you do it? So what I did was, I created dummies here in Stata to create dummies for a variable. You type in tabulate the variable, comma, generate, and then you have like what the variables are going to be called. So I had DD. Okay, so this was DEDD start. So here we have, I created 48 dummies. Why? Because time till has 48 values, -24 all the way to 23, including the 0 is 48. So there's 48 values to this time till, and I created dummies for all of them. DD1 is a dummy for, do you have a time till value of -24 all the way down to DD48? Okay. Now, I know from the label what each of these is going to be. So I'll just run a regression. This is in the Baker data. I'll just run a regression of state and year fixed of firm and firm fixed effects, year fixed effects from DD1, drop DD24, and then go on. So I'll go like this. I'll go A reg Y. Is it Y or Y2? Y. So I'll go A reg Y, I dot year, DD1, DD23, DD25, DD48. A ID cluster state. All right, so let's do it like that. So that'll give me here the year fixed effect. There's the year fixed effect. There's the panel fixed effect right there. And here's the dummies. Okay, so I'm going to run that. And this will give you right here, you'll get, I'll get a bunch of coefficients on the fixed effects of the year. These are getting suppressed. You can, yes, you can, German. It'll take a long time with this one because of how many, it doesn't report the fixed effects on it. So, it does it in the background. But here's my event study leads and lags. There's a lot of collinearity things that are causing it to drop out. But this is the leads and lags, okay? And then you would just plot it. Traditionally, if you're doing two-way fixed effects and relative event time, diff and def, and you do two-way fixed effects, that's what you would do. And you get these coefficients that are not zero. None of them are zero in this data. Even though I know from the I know from having generated the data that there are no treatment effects for anybody pre-treatment. Everybody pre-treatment, there are no treatment effects. But when I do this specification, weirdly enough, I'm not finding zeros. Okay, I'm not finding zeros. And the post-treatment starts at DD26. Okay, and I know post-treatment, everybody has positive treatment effects. Okay, everybody has positive treatment effects post-treatment. But when I do this regression, I'm not finding positive treatment effects. So I could literally like run it like this. And I'm not finding like what I know is true. I'm not finding what I know is true, right? Like I may not know the correct regression specification, all right? But I know pre-treatment, there are no treatment effects in this data set that I generated, this simulated data set that I've generated. And yet when I run the regression, I'm getting point estimates that don't make any sense. I'm finding pre-treatment non-zero coefficients, and I'm finding post-treatment, like I'm not finding any positive ones, even though that's like exactly what's true in the data. That is exactly what is true. Like if I was just to, you know, think about an event study, okay? Think about an event study and ask myself, what would I want an event study to mean, right? Probably I'd be thinking something like this. I'd be thinking, all right, well, what's the treatment effect for the treatment group units in the pre-treatment period in T-1? It would just be an average over everybody's T-1 treatment effect. It would seem like it should be a 0. Seems like it should be a 0. Like that's what I'm trying to measure, right? Like I'm trying to measure in this T-1 graph here, this T-1, I would like a point estimate that corresponds to a treatment effect value for that year. And in an event study context, that would just conceptually be an average of the treatment effects in that relative time period for those groups of units. Okay. And a regression is supposed to represent treatment effects. And this graph is supposed to also be interpreted correctly because look, pre-treatment, the treatment group units allegedly are not different from each other. Post-treatment, they are. So presumably, like I should be able to like look at the gap and interpret it as a treatment effect. And in a regression, right here, you would think that that would be like that 0 would be something like this. So I ran that regression with my birth county data, ran that regression. I found this same thing, found the same kind of picture to what I'm finding here with the Baker data. Pre-treatment, I found all these positive terms right here. Okay. Here I don't have any confidence intervals because everything's month, because it's a 30-year panel, or the 30-year panel with differential timing means that in relative time, it's even larger. So it's only 30 calendar years, but in relative time, it's like 48. And I'm not finding stuff that even when I programmed the data myself, I know that the treatment effects are 0 for everybody pre-treatment, but I'm not finding that in my regression. Found the same thing here. It won't be weights. That's where, well, weights are ironically causing the problem. But that's what we want to look at, that with Son and Abraham, is why is this happening? And it's happening because of weights. It's happening because of weights that OLS is placing on the estimated treatment effects. It's the same kind of thing that was happening yesterday with the static specification, but now it's also doing it inside the event study. So this is the point, is that this specification with differential timing is going to have its own problems. It's going to have its own problems. And one of the things that can happen with using two-way fixed effects is what happened to me, which is when me, Melanie, and Christine looked at this regression, okay? When we looked at it, I showed this to them and I said, we don't have parallel trends. We don't have parallel trends. So even though we had been finding this result, and we had been presenting, I mean, I actually think if I look here, we presented it at ASH. This is like, this is the whole research. This is like the whole layout of the ideas. Like Atlanta in 2001 has no personals. There's the personals. That's it. Atlanta in whatever year this is, all of a sudden it appears. And then we like went through. Well, that even looked better. So here was like the way that we did it. Randomly assigned the dates of treatment. We also checked the leads and lags. We see less persuasive evidence of parallel trends. And so, we were finding this kind of thing. And so we were less optimistic. But at this time, 2018, we didn't have any other options to do anything, or I didn't know anything at this time. So we found these large, huge, really, really big ATTs, and you can see this kind of like style. And we put the paper down here. When we ran this, we put the paper down. And we put the paper down because I was like, well, we put the paper down because exactly this right here. Like we just really had no good evidence of parallel trends, so we put the project down. But the thing is, like in the Baker simulation, I know I have parallel trends. I know I have parallel trends, is the weird thing. Like I know if units had never been treated, then they would have just grown by a rate of n. And so it's like, and pre-treatment, there is no treatment effect. But at the time, when we did this project, I just didn't really know what else I could do, so we put the project down because we thought that we had no parallel trends. And so we only just recently went back. We've only just now gone back to the project and started over using the more we've now are using, this is now 2023, we're using the new methods. And when we use the new methods, we don't find that. We find using the new methods that the pre-treatment leads actually were flat. So what's going on? So what is going on? Why is it like this? Why is it like this? Andrew's paper does not analyze the event study. Let's return to that question, German. That's a good question. Sometimes it's probably if the abundance of evidence, in a meta-analysis kind of sense comes from differential timing, diff and diffs, and they use two-way fixed effects. We should probably summarize everything that we've learned to try to think about, how what exactly to maybe go back. But it might be that some of these need to be reevaluated for sure. Andrew Baker has a paper where he does that with a lot of finance accounting papers, and that it used staggered rollout. And in fact, it did matter. It did matter a lot. But I've seen in poli-sci, someone did that and it did not matter. But these are all no one's done a full exhaustive project. It's very, to look at every, top 5 or something like that. But that would probably be worthwhile. And I know that some people, yep, it sure is. It's here. Andrew Baker. There was here. Publications. It won this one. It won corporate finance paper of the year. And in it, how much should we trust staggered diff and diff? And it's inside our readings. It's inside our readings here. You can find it. They reevaluated they re-examined and they found that in many cases, the new diff and diffs found substantially different results. So it can matter. It can matter a lot. Okay. But what we want to understand now with the event study is, why does this happen? Why does this happen? Like what is it that is driving this pattern? Okay. Why is this happening? And what about if I don't have heterogeneity, and I find these kinds of weird things too. So like what exactly is driving it? Right. And that's where we're going to start up. We're going to look at this analysis that was done by Sophie Sun. I think she's at Semfi now, maybe, or I'm not sure where she is. She was in Madrid, so, but I think I might have read that she might be relocating to Bocconi or something like that. Sophie Sun and Sarah Abraham. We're going to look at this paper by Sophie Sun and Sarah Abraham that's usually just called Sun and Abraham. And it was prompted, the paper was prompted by a random comment that was made in their public finance class by Amy Finkelstein. Amy Finkelstein, the John Bates Clark Award winner and MacArthur Genius Award winner, was their professor of public finance at MIT. And she made a random comment. She said, I find different results. I find different results depending on whether or not units are treated. Sorry, I find different results depending on if I use the T-1 or the T-2. She makes some comment like that about what happened, and then just goes on with the lecture. Sophie and Sarah then sit down and work together to figure out what is being estimated with a two-way fixed effects dynamic specification. And this classic paper comes out of it. All right. So they don't use the Frisch-Wald level theorem to do the decomposition. They use something called the omitted variable bias formula, but they nevertheless kind of get to the answer. But unlike Andrew, they are going to come up with a solution. So it's going to be this paper by Sophie and Sarah do two things at once. They're going to analyze the problem of the two-way fixed effects estimator, and they are going to come up with a solution. So when we come back in 15 minutes, we'll go into that paper and see if we understand it, and then understand the solution. So we'll come right back. All right. So let's look at this. So this is a technical, that was like a soft launch of the thing. So here's the big ideas. I keep having the dates wrong, but the paper has two parts. It's a decomposition quote. It's trying to figure out, here, why is this plot wrong? It is wrong. These coefficients are not true. There is the treatment effect in the 20-second lead pre-treatment is not 98. Treatment effect is 0. Okay, so you can see it here. So you can see it. We know it because we generated the data. Pre-treatment, there are no treatment effects. So these should be 0. So why are they not in this standard specification? So they're going to decompose the leads and lags. All right. Then what they're going to do is they're going to show it's in it. And then a later paper by Paul Goldsmith Pinkham, Peter Hull, and Michael Kolsar shows that, what the solution that Sophie Sun and Sarah Abraham kind of find, or not solution, their analysis kind of holds more generally to all OLS when you have multiple treatments in the same specification. There's these contamination problems that the model has. We're going to look at that too. We're not going to look at it too, but we're going these two are kind of connected. Okay. Yeah, these might be the same thing actually. And then they're going to develop a new estimator. Okay. And this estimator is identical to what Callaway and Santana presented. It's the identical estimator, except for a couple of things. Their analysis will only use the last cohort as the treatment group. As the last cohort treated will always be the comparison group, unless you have a never treated group, in which case the never treated group will be the last cohort treated, or will be the comparison group. So if you remember Callaway Santana, they would do all their estimation. They would use the not yet treated as a control. Sun and Abraham will not use the not yet treated. It will use the last cohort treated as the control. So it's only one not yet treated, and it's the same group every time. So that's one of the things that makes their paper different, is they do not have this rolling, changing control group for each of the parameter estimates. They have the same one. And how they handle the covariates is going to be different. They're not going to do all this doubly robust stuff. And then they're going to bootstrap the variance of the estimator. And so that'll also be a third thing that's different. But otherwise, it is identical. So if you have no covariates and you have a never treated group, it will be identical. It'll be the same point estimate with a different variance coming from the way the bootstrap and the analytical standard errors are calculated. But otherwise it'll be the same. Okay. And usually confidence intervals won't be too different. They'll be pretty much the same. Okay. Here's the big picture. If you have what is called homogeneous treatment profiles, which I'm going to start out and explain what a homogeneous treatment profile is before we even dive into all the math. If you have homogeneous treatment profiles, then none of this will happen. None of this will happen if you have homogeneous treatment profiles. All of the treatment effects will cancel out. Okay. But if you have heterogeneous profiles, they won't. So we got to figure out what that is. All right. But that's what drives the whole problem. The whole problem is coming from, well, and you get this kind of thing. You get this kind of thing with, it's not heterogeneous treatment effects per se. It's how the treatment effects differ for the groups. It's a little bit different. You can have heterogeneous treatment effects. You can't have heterogeneous treatment effects across the groups. That's slightly different. Within a group, you can have all this heterogeneity. It's the fact that you have different average treatment effects for every, county that gets treated. That's the problem. Okay. So let me show you what I mean by a treatment effect, homogeneous treatment profiles versus heterogeneous treatment effect profiles. So when we go over here, and I'll just look at this diff and diff exercise again. We'll go over here to this event study. Okay. We have here in this event study dynamic treatment effects. And the dynamic treatment effects we were talking about was that they were changing for a given group. Okay. Changing for a given group. Going up over time versus constant. Within a group, they're the same. Constant, dynamic. All right. So that was what we talked about mainly yesterday, was that this dynamics at all, any dynamics at all, created the problem, right? Even if the dynamics were just here, it created the problem. What the event study stuff is not going to, with Sophie Sun and Sarah Abraham, it is not a problem for OLS. for these coefficients. These coefficients, the problem is not because of dynamics. That is not why we find this and this. That's not what does it. Okay? What does it instead is if the dynamics are different for every group. So see here, these dynamics, this treatment effect profile, it's the profile of the 86 group. This profile shows treatment effects going up by 10. These show treatment effects going up by 8. These show treatment effects going up by 6. That's heterogeneous treatment effect profiles. Okay, I should even write that down. So I say homogeneous treatment effect profiles. I should say heterogeneous treatment effect profiles. Okay, this is what homogeneous treatment effect profiles would look like. Okay, and notice what changes over here, right? Essentially, what changes over here is that these event study treatment effects, these average treatment effects, all of these are the same, right? They're all the same. Everybody's just going up by the same amount. So it's a version of homogeneous treatment effects. It's like homogeneous treatment effects across groups. That wasn't a problem with Andrew. Andrew's, if you look back to what Andrew's was finding, right? When he was doing this analysis here of that coefficient, was no leads and lags, it was one dummy. And what he was finding is that, that contains a weighted average of average treatment on the treated for every group. And these could be different. But they would be like inside that number. What was giving you the problem was the dynamics. The dynamics were getting negatively weighted. Okay. That will not be an issue here. That is not what's going to be the issue. It's going to reverse. Now what's going to happen is that the dynamics are not the problem. The dynamics are not the problem. The problem are the differences in the dynamics across the groups. That creates the problem for the event study. Okay. All right. Now the notation gets a little bit challenging, so I just want to go slow. I do want you to learn this. I do think it's important to know the reasons that the bias is there. All right. So what usually people do, what oftentimes people would do is they would bend the data. What does bending mean? If you look back at my Craigslist project, my data was in months. Okay. These were like I had monthly data. But when I ran my regression, we would bend, or I bend it, and where every dummy was a dummy for a 10-month period of time. So every coefficient was equal to 0 or 1 for many observations. That was the bend. Okay, so I had a dummy for, is it 10 months prior to treatment? Is it 10 months post-treatment? And so I would have 10 different months in a single dummy. So there was a bin, and the bin was called G. But inside the bin are individual leads and lags. And so here, and those would be L. So this would be like a bin of -1. It would equal 1 if it's 10 months prior. It was in 10-month blocks. It would equal 1. And inside that 1 were 10 separate months. That was this, like right here. I just did it this way. I did it this way because this was so crazy. To have put up 100 coefficients was going to be bad. Just like, this actually, I don't even have any confidence intervals, and it just gets so noisy. And maybe I shouldn't have put those numbers there, but it can, so for aesthetic reasons, I bend it. Okay. So with that in mind, many people bend. All right. So they're going to have different notation. the letters are going to be referring to binning, G, or what's inside the bin, L. Okay. If you don't bin, then G and L are the same thing. Okay. So if you don't bin, if you just simply were like, so right here, I don't bin. So I have dummies for every single relative time period. So here I only have the leads and lags. But if I had done something where I was like blocks of, blocks of 3 or 4 years or something like that, and within that was, each of these individual leads and lags, then you would have the large number of the set, and then you would have however many are in there. All right. So that can create a little bit of some challenge because they show up here. All right. L shows up here. So I'll try to, refer to that every now and then. And if ever you get confused, just raise your hand and we'll go back on it. Okay. Secondly, all right. Secondly is the parameter. Now, what we had here was the group time average treatment on the treated. That was what Callaway Santana called it. The group time average treat on the treated. Because these were all graduate students and they did not know each other, they all sort of end up kind of in reinventing the same concepts. So Sun and Abraham don't call it the group time average treat on the treated. They call it the cohort average treated on the treated. And so this is a cohort. It's the 1986 cohort. It's the 92 cohort. But Callaway and Santana called it a group. It's the same thing. Okay. It's the same thing. And Callaway Santana call it group time average tree on the treated. They're going to call it cohort average tree on the treated. And then the subscript is going to be the event year and which relative time period it is. So this would be like CATT. It would be like CATT. This would be like an E, and this would be like an L. All right. And the E refers to 86, and the L refers to the relative time period. But see, so it's like this says L, okay, but it won't say 1980 for this group. It would be the T minus 6, T minus 5, T minus 4, 3, 2, 1, 0. But they're gonna like rather than have so it's like basically this would be T minus 6 all the way to T plus, whatever that is. But it's like you wouldn't be able to make this kind of thing. Okay. You wouldn't be able to make this kind of thing because what you would have instead, if you did it, was you would have this kind of thing. So you would have here. Okay. So it's like relative time. And this becomes the CATT for that group. And then this becomes relative of time. And this becomes the CATT for the 992 group. And it'll be like, this kind of thing. So let's say it's like here. Like that. So this versus, versus this. Right. So this is like how this is called group time. And then this is called CATTEL cohort ATT. Right. But otherwise, they're the same thing. Otherwise, they're the same thing. Right. They're just going to be labeled differently. And, it wouldn't be as easy to create it wouldn't be as easy. Wouldn't be as easy to like create a single. I don't think you could create like a single table, you know, using this kind of syntax, this kind of notation. But it would be the same thing. Okay. All right. Well, so then what's our goal? Our goal remains the same. Our goal is to literally estimate all of these, every single one of them. Our goal is, if we want to get all of those, all of those, all of those. We're not going to use as a control group anybody that's treated. So we're going to only use the last cohort as the comparison group each time. So when we're estimating the 86 cohort ATTs, we're always going to use 04 as the control group. Callaway Santana uses, if we're trying to get this one, it uses all three of the groups as the control, not yet treated. Sun and Abraham only uses the last cohort unless there is a never treated control, in which case, if there's a never treated control, then it'll use those. Okay, it'll use those then. But otherwise, otherwise they'll, it's going to be trying to tackle them separately. All right. So we are going to try to get all of those using the 2004 group as the control. We're going to use all of those separately using the 2004 group as a control. We're going to do them separately 60 times or whatever the number is. Okay. And then the goal is to interpret it, is to both get it correctly using their new estimator, but also interpret what two-way fixed effects does. And their focus is on irreversible treatment. They're not going to do the switching. This symbol of the infinity symbol shows up. I don't know who it starts with, but they all start using it, all these econometricians, and now it's standard. It shows up. It's referring to a particular kind of counterfactual. All right. It's referring to a particular kind of counterfactual. So I'll just use as an example here. Let's say German, right? German is getting a PhD, right? German is getting a PhD. Or happiness with a PhD is Y equal Y1. Happiness without a PhD is Y equal Y0. But in the event study context, for reasons I don't fully, the econometricians become very precise about which Y0 is it, right? Is it exactly? So German could either delay getting the PhD or never get PhD. And if German delays getting the PhD, then how long did German delay? Right? How long did German delay? So let's say that German's treatment date is 2020 for the PhD, right? German's treatment date is 2020 for the PhD. German's counterfactual is what? German never gets a PhD. and therefore happiness is y equals y infinity. Versus German waits to get the PhD in 2021. German waits to get the PhD in 2022. German waits to get the PhD in 2023, and so on. I don't know exactly when this starts. I think it might be Jamie Robbins is the one that does this kind of notation. Again, I haven't paid full attention to when I've listened to them talk about it, but I believe that's right. So they have to describe, precisely what counterfactual there is, since there's like an infinite number of them. Even for German, there's an infinite number of counterfactuals, because you could imagine German waits milliseconds to get the PhD compared to then. And so, they've got to say, no, we're going to be talking about one single counterfactual. And that counterfactual is going to be, we're going to be comparing treatment effects. All right. So the causal effect of the PhD on happiness will be defined for German as this: delta German equals y1 German minus y infinity German. Means causal effect will be happiness with a PhD in 2020 minus happiness without ever getting a PhD but observed in 2020, right? It'll be that, or observed in a given year. That's what we're going to be referring to. So this infinity symbol is, probably worth just kind of slowing down and looking at, but it's a particular kind of potential outcome. All right. It's a never treated counterfactual, right? Okay. So treatment effects are going to be defined at the individual time period level as what happened minus the never treated counterfactual. And then we're going to take the average of the treatment effects at a given relative time period across the units treated at that time to get an average tree on the treated. So that's all I mean here. All I mean here is when we take the average of the treatment effects at a given relative time period, okay, for people of the same cohort, E, so that's the 86, that's the 92, and each of these numbers is the average of the treatment effects for that group in that relative time period. That's what we mean by CATTEL, E86, E92L, referring to this part. Okay. Oh, hey, Kyle. Kyle's here. So, all right, we're done on this. So here's the definition. So we have here definition 1, cohort specific ATTL, periods from initial treatment date. So here we have CATTEL. It's referring to this, CATT86L, CATT92L, is defined as outcome minus counterfactual. So this right here, this 10 is defined as, outcome minus never treated counterfactual. Never treated counterfactual. So in my data, I believe in my data, it's going to be list, group, list, state, treat, Y0, Y2, and 1 to 10. Okay. So here we have Y. So we'll make it like Y2. Okay. That's Y. And that's the never treated counterfactual. That's Y0. Right. And for a given group. And this is the treatment group 86. Right. So the treatment effect would basically be You know, and I actually can make this. I could say gen delta equal y2 minus y0. I could say, let's say, here we go. ID, year, treat date, treat, time till. Okay, so I think this will work. Oh, and then I need delta. All right. So in the pre-treatment period, I've got 0 treatment effects because it's identical. And then in the post-treatment period, I've got a treatment effect that's around a 10. And it stays the same. Stays the same because it's the constant. Y2 is the constant treatment effect one. Versus gen delta equal y minus y0. And then I could list that. And then you see the dynamics, 10, 20, 30, 40. Okay. All right. So that's what our definition is, a cohort specific ATT. And what we want to know first is, well, under what conditions will two-way fixed effects be unbiased? Right. So let's look at assumptions. Parallel trends. Parallel trends is with respect to the infinities. So we've got are all of the average potential outcome, average y0, the average y0, is the change in the average y0 the same for every group? It is in our data because y0 is growing at the same rate for everybody. Everybody starts at a different point. The intercept is different, but everybody grows by 1 plus E, where E is on average 0. All right. And N is just N here is, just a counter. How many years has it been? Okay. So we have built into the data parallel trends. Okay. So that's true. All right. No anticipation is also built in. We can see that here because at baseline, Y equals Y0. You can see that. So we have also built into the data that Y equals Y0 at baseline. There's no treatment effect. Okay. All right. So we have no anticipation in the data, but we don't have treatment effect profile. So if I was to just by sort group, summarize delta. This isn't the easiest way to do it, but you can sort of see here. All right. Group 1's average treatment effect is 100. Group 2's average treatment effect is a 45. Group 3's average treatment effect is a 15. Group 4's is a 3. Right? That's not telling me the dynamics, but you at least see there's heterogeneity in the simple way. You can see heterogeneity across the group. But we can also see it, here, like the treatment effect profiles. The dynamics of this one goes up by 10. The dynamics of this one goes up by 8. That's why they're different. So we do not have treatment effect homogeneity profile. If we had treatment effect homogeneity profile, then this would also go up by 10. This one go up by 10. That one would go up by 10, but we don't have that. Okay. So because we don't have it, two-way fixed effects will be biased. But if two-way fixed effects was not biased, if two-way fixed effects did have it, then it would not be biased. And here's why. So we're going to run this dynamic event study model. And what we want to know is about each of the coefficients. So when I say mu G, okay, what am I talking about? I'm talking about one of these 48 coefficients. So this coefficient right here, it's the -10 coefficient. It's equal to 67, right? So if I was to write it down, so for the mu -10, it's equal to 67, positive 67. The actual CATT for, E -10 is a 0 though. It's a 0. So for everybody, it's everybody in the data. everybody in the data is a -10. Like I can see that. Sum delta if time till equal -10. It's a 0, right? The average treatment effect at relative time period -10 is a 0. But the regression coefficient is 67. So why? Why is it not correct? Right. So we say, all right, well, let's just like put that right there. Okay. This is a 67. It must mean that all of this sums to 67. Okay. All of this must be summing to 67 because this is the decomposition. This is Sun and Abraham's decomposition of each of those leads and lags with differential timing. All right. First is the targets. They're going to find that each of these coefficients here, each of these coefficients is equal to the sum of 3 weighted averages. Every inside each of these rows is a diff and diff. So that's the thing to point here. This right here is a 4 averages, 3 subtraction kind of deal. So look closely at this. That minus that, right? So this right here is, you know, after minus before for the d equal 1 group. And this is after minus before for the comparison group, right? So for the comparison group. So, and what you're saying is that this is just a diff and diff. So it's not causal, it's just a diff and diff, right? And it's basically after minus before baseline untreated baseline. That's what they're doing right here. Minus after minus before for baseline, diff and diff is it. But we've got this weight on the outside. What's this weight? So the weight's over G, all right? And what it is it's basically saying that for each, like if this is a bin, if this is a -10 and it's binning, and inside that -10 is like 10 different months, like the way I was doing it with the Craigslist paper, then you've got essentially 10 diff and diffs referring to each subsequent, you know, lead or lag, all grouped into a single bin. Okay. And so this weight here is a positive weight. It's a positive weight that sums to 1. Right. So it's basically saying what it would basically be saying is that this coefficient right here, 67.25, is partly a positively weighted average of diff and diffs inside of whatever that bin is. But that bin of -10 just is equal to the lead, the -10 lead. So there actually is no binning that occurs, which means that's just going to be a 1. Right. It's going to be one single diff and diff. Plus, the 67 will also contain the diff and diffs from every other treated group that's eventually going to get treated compared to the same, for the same thing. So this would be like, you know, inside that number would be like, well, we don't know yet the causal part, but it's going to be basically equal to this one. And then it's also going to be based on information from this one. And it's also going to be based on information from this one and that one. So these are the contamination from the other groups, the other leads and lags. Okay. And then last is contamination from the dropped periods. Okay. So what we have here is the excluded group is going to also be the diff and diff. OLS is going to calculate diff and diffs, 3 separate types of diff and diffs, and put them into each lead and lag, right? These weights sum to 1. These weights sum to 0. Now, the only way weights can sum to 0 is if some of the weights are negative and some of them are positive. It's the only way that it could ever do that. And then these weights sum to -1, right? So look, let's look at what do we get if this is true, okay? And this is without any assumptions. This is just mechanically what's going on. This is like the Bacon decomposition. No causality, no bias, just each lead and lag is a sum of all weighted diff and diffs. Again, it's the same kind of thing. Now let's invoke parallel trends. Let's invoke parallel trends. All right. So if we invoke parallel trends, every diff and diff then turns into a causal interpretation. Okay. So now we see that under parallel trends, this -67, this +67 is equal to a weighted average of treatment effects. It's a weighted average of treatment effects for in that period, plus a weighted average of all the other leads and lags, which we know from here. Like if I'm trying to figure out the treatment effect for that particular number, and it's going to be biased by all the other leads and lags, that's what it's saying. It's like this will be that number plus all the other leads and lags. It's getting absorbed into it. That's why basically what's going on here is that because even though that is actually a 0, the regression coefficient is getting all the other leads and lags beyond just the 0. So it's like that might be a 0 right there, but it's getting the 0 and it's adding in all the other leads and lags. Causal effects. Weighted, where the weights sum to 0. Some of them are positive and some of them are negative. Plus, because regressions will always drop one lead or lag, I had to do that here. Okay, so like when I ran this regression here, when I ran that regression, I had to drop DD24 because of collinearity has to drop stuff. So I dropped DD24. There, it's not there, right? Whichever variables are getting dropped for the relative time periods, those are also, their treatment effects are also getting built into here. Okay. So I'm going to go straight to an example. All right. Let's say we have a panel, 2 years, but cohorts are getting treated at different time periods. One gets treated in the first period, one gets treated in the second period. Okay. And since we have 2 calendar years, that means we have even more relative time periods. So it's in the same way that we have, 30 years of data, right? So this goes from 1980 to 2009. With differential timing, we have 48 different relative time periods. Okay, we have 48 relative time periods because if you look back here, okay, we've got, this group goes all the way back to -12. This group only goes back to -6. This group goes all the way to 17. This group goes all the way to only goes to 11. So it's like, basically you get the longest post-treatment number possible and you get the longest pre-treatment possible. And, we have a group here that's got, how many is that? So that's count. They've got a -24, right? They've got coefficients that go all the way up to -24, but their post-treatment only goes to 6. This guy only goes -6 pre-treatment, but post-treatment, it goes +24. So you can see here, we only have 30 calendar years, but we have 48 relative years, all right? But not everybody has something that goes back that far. That's why there's only 250 that have a -24. But all the firms have at least 6 pre and at least 5 post. Okay. So we're going to have here the same kind of thing. We're going to have 2 calendar years, but it's going to give us, it's going to give us, one group that's going to go all the way to -2 and one that's going to go all the way to 1. And the reason why it doesn't go to 2 is the same reason here. This goes from -24 to 23. And that's because we're going to include a 0. So it'll be a little bit different, but we're going to have illustrative purposes. What we're going to do is we're going to run this regression, or we're not going to run the regression. We're going to do the decomposition. Okay. And I'm going to imagine running a regression and we're interpreting the -2 lead. All right. We're going to be interpreting the -2 lead using this framework. And so we're going to go, all right, well, how many, if I drop in my calculations, let's say that I just, in this regression, I drop my -1, okay, -1, just like I did here. All right. So when I ran this regression, I dropped t-1. DD24 is t-1. So I'm going to drop my t-1. But what if I dropped my t-1 and I dropped my t+1? What if I did both? Okay. What if I did both? So that's what we're going to do. We're going to drop 2 of them, one pre, one post. And we're just going to see. You could be like, why are you doing this? We're doing it to see. We're doing it to understand what will the t-2 coefficient equal. That's all we're trying to do. We're just trying to figure out what will it equal. And it equals a weighted average over the target relative time period, which is -2. There's only one group that has a -2, and that's group 2. Right? So it's always for these long relative pretreatment periods, the only groups that ever have them are your later treated groups. So like, this right here is, CATT 1992L, right? And this is the CATT, 1986L, right? And so for the 2 groups, okay, the further back, the later that you're treated, the more pre-treatment leads that you have. I know this seems obvious, but it actually can confuse people. And the earlier that you're treated, the longer your post-treatment lags will be. Okay, so that's just something for you to realize. So if I have here the -2, okay, it's like having my -12. Well, this guy can't have a -12. This guy does. That's why there's only the second group that has that. All right. So when you're estimating that coefficient, there's only one group with it in this data, and that's my later treated group. So it would be like if this was a -12, it would only be coming from the later group. And it's going to be a 0. All right. Is what we're going to do is we're going to be assuming this no anticipation. And what no anticipation is going to do, once we assume it, then everybody's pre-treatment period, anybody with a negative in this second number, that'll always be 0. So no anticipation means you are not treated in the pre-treatment period, which means the treatment effect is 0. Okay. So we're going to just now start crossing stuff out. So under no anticipation, all CATTs will equal 0 for the pre-treatment period. That's this one. Okay, so that'll be a 0. That is not affected by no anticipation. That is not affected by no anticipation. That is not affected by no anticipation, but that is. These 2 are. So what are these? These are the omitted excluded bins. We said here that we are going to drop -1 and we're going to drop 1. Okay, just like I did in this regression, I dropped DD24 and I dropped DD25. DD24 is pre-treatment. It's negative, so it's the -1. So it will get the we know its CATT is going to be 0. So I'm going to go ahead and say those two are going to be 0. That's minus 0 minus 1/2 times 0. Okay. So let's just like look at it real quick. So that's a 1/2. So let's just like actually do a couple of things. First of all, we said those weights sum to 1, those weights sum to 0, those weights sum to -1. Right? There is no weight visible there, but that's because there is no binning that's occurring. So that's a 1. That's a 1 right there. These weights on the included bins, these are supposed to sum to 0, and they do. 1/2 minus 1/2 is a 0. And then these weights are supposed to sum to -1. 1/2 minus 1/2 is a 0, minus 1 is a -1. So there's the weights. Okay. No anticipation eliminates anybody who has a it eliminates all of the parts of the decomposition that are bringing in the negatives, okay. So we've got here we've got those, all right. And then secondly, so that's no anticipation. Parallel trends is what turns every diff and diff into a causal term. And then homogeneity, right? So what does homogeneity do? Homogeneity means that the CATTs are the same regardless of group for a given relative time period, L, right? So it would mean CATT 10 equals CATT 20 under homogeneous treatment profiles, right? That's what that would mean. But if we look at our data, right? So like, let's look at let's look at, number 4, right? Let's look at lag 4. Well, for the 1986 group, it's a 50. And for that, it's a 40. Okay. So if we have here this 1/2 times 50 minus 1/2 times 40, that's going to be 25 minus 20. It's going to be 5. Under homogeneous treatment profile, though, that would mean this. And that would be 1/2 times 50 minus 1/2 times 50, which is 25 minus 25, which is 0. Okay. So under homogeneous treatment, under parallel trends, all of these are causal. Under no anticipation, that's a 0. That's a 0. And that's a 0. Under homogeneous treatment profiles, that's a 0. But that will not be a 0 because we included in the regression an omitted category of a post-treatment period. And if the treatment effect is not 0 for group 1 in the post-treatment period, then even with no anticipation, parallel trends, and homogeneity, this will still not be unbiased. But that just means don't. So the solution here is, this is why you don't put in your regression specification, you don't drop a post-treatment dummy. You don't drop it, because what happens is it just ends up getting built into the bias. It gets built into the bias. So you just don't drop them. You don't drop them. You only drop the pre-treatment baseline values. The pre-treatment periods dummies are the ones you drop. And since if that's what you did, then there wouldn't be in the excluded bins any post-treatment, so they wouldn't even be there. And so if you have treatment effect homogeneity profile, that'll eliminate this one. If your omitted categories are all pre-treatment, then under no anticipation, those will also be 0. And then this part will just be whatever it is. Whatever it is. If the CATT is 0, then that'll be a 0. And if the CATT is not 0, then that won't be 0. And that's how it is for every lead and lag. So the reason why we're getting this weird result right here is we have parallel trends. We have parallel trends. It was built into the data. Okay, so we have parallel trends. And I dropped only the pre-treatment period. So all the pre-treatment leads were, all the pre-treatment treatment effects were 0. And I excluded only pre-treatment period. So this whole part was mechanically 0 in the decomposition. This was a 0 in the decomposition, but this wasn't, because I have heterogeneous treatment profiles. All right, I had heterogeneous treatment profiles. Each of the leads and lags are being added in this grouped way, and they're not the same. So they're not canceling out. They're not canceling out. So so that's the source. The source of the bias in anybody's event studies, okay, with 2A fixed effects and differential timing, the bias is coming from the treatment effects leaking in, contaminating. Treatment effects from every other relative time period are leaking into each indicator. They're leaking into each indicator. So what do? They propose a version of Callaway and Santana. They don't call it that because this paper came out at the same time. This paper came out in 2018. Callaway Santana came out in 2018. Andrew Goodman Bacon comes out in 2018. They all but they're just being posted. I don't know where they're getting posted. This paper does get cited in a paper by Singes et al. In their minimum wage paper. They'll cite it. People that were at MIT seemed to cite this one more often. Callaway Santana is the Vanderbilt group, and it's not on people's radar as much. But this one does get cited. They propose a 3-step interacted weighted estimator, IW. But all it's going to be is diff and diffs. All it's going to be is diff and diffs, calculating diff and diffs for what it's going to be basically is it's going to be getting all of these. Again, just like Callaway Santana did, it's going to get all of them, and then it's going to aggregate them. The weighted part, it's going to aggregate all of them. But they're only going to use, as a control, one group the whole time. Step 1, they're going to say, do this regression, okay, for every single relative time period using the never treated or the last treated cohort. Anybody that's already treated, it's going to always get dropped. So they're going to do diff and diffs. They're going to do diff and diffs, but they're going to do it for every single one of these. So it's like over here. They're going to be getting that one using 86 compared to the last cohort. This one, 86 compared to the last cohort. So that's that dummy variable. If you are in that particular group, compared to a last treated cohort or a never treated cohort for a given relative time indicator. So they're doing this regression. They're going to do it, for this group, they're going to do it 23 times. For this group, they're going to do it 23 times. They're going to do this every single time for every single group. And when they do it for every single group, they're going to get all of the, they're going to end up getting 69 separate coefficients, 69 separate coefficients. But it's really just all coming from them using, these are just simple diff and diffs. It looks fancy, but all it is just a simple diff and diff. Then they're going to get weights. Once they get these numbers right here, they have to decide how they're going to weight them. Well, in my example, there are 250 firms in every group. So the weights are going to be the sample shares of each cohort in the relative periods, and it's going to be all weighted the same. And then once they've got all 69 of these, they average them. They average them. And this part is the interaction weighted estimator, right? So it's like, here is step one, get all 69 of these. That's step one. Okay, so that's step one. Step two is figure out what the weights are. So I'm just going to do simple weights because all my firms are the same. And then step three is do the weighted average. Yeah, I'm gonna tell you a little bit, German, of my opinion about that. I'm gonna tell you at the end of the day. And then the last step is all three. Weight them together. And this right here, this V hat G is basically this. This would be like Son and Abraham, all right, which would be the estimates of all, 48 or whatever it is, however many, of these there are, of the feasible leads and lags. It would be, all of them, but it would be the relative event time. So under parallel trends and no anticipation, that's all you need. You don't need any statement in order to use Son and Abraham. You don't have to restrict the heterogeneity. You don't have to restrict the heterogeneity at all. The heterogeneity was only a problem with two-way fixed effects. Well, no, it doesn't. It doesn't mean that. Homogeneous treatment effects are not about the time periods. It's about the whether or not it's really more about the selection. Do you think that the groups have different treatment effects? Okay, it's not about the dynamics. It's about the groups. Do you think that the groups have different treatment effects? Yes, it's about the cohorts. It's about the cohorts. It's not about the treatment effects. It's about the cohorts. Do the cohorts have different treatment effects? If the cohorts have different treatment effects, then what happens is the bias comes in here. The bias comes in here, and you end up with some weird negative weighting because look how this is positively weighted, but then this is negatively weighted. So some of these groups get negative weights and some of them don't. And that's where the bias is coming in. But Callaway, Santana, Son and Abraham basically just, this ends up this doesn't matter. This is irrelevant. This does not enter in. This is only coming from the two-way fixed effects. So they end up with this, interaction weighted estimator. I'm not going to do it, but I want to show you right now how to do it. Okay, I'm going to show you how to do it. It's in Stata and it's also in R. Right, so I'm going to show it to you in R, and then I'm going to I'm going to show you a bunch of stuff. So here, inside this fixS command, which was the one Kyle was saying is his favorite package, it's this guy, single person that made it. It was just labor of love, I guess, for him. And then a couple of other people came in and helped at the end. fixS. We're going to pull fixS in. Okay. And what's cool about fixS is fixS has in it it's actually a fixed effects estimator, and it's got high dimensional fixed effects estimation, very fast. And you can sort of see it broken down by how fast it gets, but it also has the regular two-way fixed effects, and it's got Son and Abraham. Because the author is an economist and the people that helped, they just built Son and Abraham into the fixS command. So it was kind of nice, and it's going to come in with this, Son Son Abraham. I guess this is Son. I don't know what the BR is mean. Abraham, I guess. I think that must be what it stands for. So, so we're going to read the data in. Okay. We're going to read the data in. That's the Haven command, Haven package. All right, so we read it in. Okay, so we got the data in 30,000 observations. Got to do the same thing again. So if we have anybody, all units in the data set are treated, so this is kind of pointless, but we need to change to a 0 anyone who is never treated, but it doesn't end up doing it, so it doesn't matter. But I just wanted you to note that here, we're going to run the naive two-way fixed effects. We've already done this. Okay, so we already did this, but you know, there's that same picture that we were getting here. Okay, so it's the same thing. It looks a little prettier because the point estimates are doing this, but we know now, we know what's going on, that each of those coefficients is equal to its own treatment effects, which are 0 plus these contamination effects, right? Contamination effects. So these contamination effects appear to be coming from the treatment effects on this side are getting like brought over here. All right. They're getting brought over here and they're coming in with positive weights, but they're like getting, but something's going on over here that clearly there's some negative weighting that's going over here. Because nothing should ever be negative. Nothing should ever be negative in our data because everything's either a 0 or it's a positive treatment effect. It's never negative, never negative, but we've got some negative weights coming in here. We've got negative weights over here too, but anyway, so we did it here, and it was just basically FEOLS outcome, and then we put in dummies for the time till indicator, which is what I did with Stata here when I ran the panel firm fixed effect, year fixed effect. So here it was firm fixed effect, year fixed effect, and I put in dummies for time till, and I dropped the -1. Okay. And I plotted it, summarized it. So we did the summary of it, and it comes out to all of these. Okay, all of those, and they're wrong. Those are not right. Okay. So then we did, all right, what is this? I don't remember what this is. Oh, this says I could just do the same thing. All right, well, forget that. So okay. All right. So then now we're gonna do Sun and Abraham. All right, we're gonna do Sun and Abraham. So the Sun and Abraham command in R is gonna be, I'm gonna call it rest cohort. And this is FEOLS. Doesn't list it. FEOLS, but rather than say dummy variables on time till, I'm going to invoke Sun and Abraham, and I got to tell it the group. So I'm going to say treatment date. And I'm going to say treatment date. Now remember, so I got treatment date, and I need to tell R to not use the I want R to use the correct control group. So I'm going to stop the data before everybody is treated. Okay, I'm going to stop the data before everybody is treated. And then it'll know to use anybody whose treatment date is later than the last year. Right. So I'm going to do that. I'm going to plot it, but I'm going to do it all at once. So I'm going to run Sun and Abraham on top of, just so you can see this, I'm going to run Sun and Abraham. And you can see right here the difference. So Sun and Abraham gets each of the coefficient plots correct. They're equal. They're correct in the sense that, you know, this is a weighted average. This number is a weighted average. It's this one. It's a weighted average over all of the true treatment effects for that period, which is a 0, which is what it got. 2A fixed effects was biased though. 2A fixed effects was coming from the 0 plus these other terms, which we're not canceling out. So that's why it pops up and it does this for all of them. And 2A fixed effects also attempts to calculate things where there is no control group. Sun and Abraham will not attempt anything unless they're at the last cohort unless the last cohort is present for that particular time period. And so it only attempts this one to here, and it gets it right. Notice how it gets it right. So we have here, let's see. If I wanted to summarize it. Okay, here's all of the coefficients I plotted over here. These are the red coefficients. In time period 0, it's an 8. Why is it an 8? Because 10 plus 8 plus 6 divided by 3 is an 8. 16, 16. These are the truth. When we get over here to t plus 6, it goes from 48. So it's always going up by 8. Okay, it's always going up by 8. But then all of a sudden, when we go from here to here, it jumps. It goes from 63. Doesn't go up by 8. If it was going to go up again by 8, it would go up to 56. It's going up to 63. How do you test it? You can use a method that's robust to it. Sun and Abraham and Callaway Santana, Borsak et al., all of these, they allow for heterogeneous treatment effects, and then you can just explore it. You can just explore it. So it's not really a test. You get literally estimates of treatment effects, and you can see if they're different. Okay, so here we see treatment effects that are different, okay, for dynamic over time. But what you would basically be needing, Winchin, is if you're wanting to know if treatment effects are different by cohort, it's just going to be a matter of aggregating. It's just going to be a matter of aggregating them. I mean, why I can show you. I can show you how you could explore, if you're what you're going to literally end up with. Correct. What you're going to end up, that's correct, Tech. So what you're going to end up with, yes, if there is only one cohort, it's a standard event study. That's right. It's a standard diff and diff event study. Just, because that's all that Sun and Abraham is doing is 4 averages and 3 subtractions. It's just doing them, group by group, cohort by cohort. See, but see, Winchin, the only way that Sun and Abraham is able to get each of these, okay, the only way they're able to get each of these is because they first got all 69 of those. Because what you're getting here, step 1, you're going to do this, 69 times. You're going to do this 69. In this example, you do it 69 times. So if you're saying, well, how do I know if I have heterogeneous treatment effects or not? Well, imagine you have this entire matrix that you just calculated, 69 separate numbers, each corresponding to a group and a relative time period. So if you want to know if you have heterogeneous treatment effects, it's just a matter of aggregating them. Like you could do an event study per group. You could summarize. You could, explore. You could get the average for each group. Okay, you could get the average for each group. There's a lot of things you could do that would let you get to that same thing. Okay. So when Sun and Abraham does it, here's the truth. All right. And that right there is the true leads and lags. And they go 8, 16, 24, 32, 40, 48. Then it jumps. And the reason why it's changing, see, these go up by 8, and then these go up by 9, and these go up by 10. Why? Because In the green zone, it's all three of those averaged together. In the orange zone, well, we lose the 98 group because the 98 group under differential timing does not have a t plus 6. It doesn't have a t plus 6 because it always uses an untreated group in that time period. And in the t plus 6 time period, it doesn't have an untreated group. So we lose immediately the relative event time, average treat on the treated for one of our groups. So look what happens when you're doing these long event studies with differential timing. This is a subtle point. So please hear me. So it's a very subtle point. When you're doing these long event studies, okay, with differential timing, the long leads start to experience sample selection. Okay, sample selection. Because notice in this orange range here, the true average is a 63. And Son and Abraham got a 63. So it is not biased. That's not the issue. It's not biased. It is unbiased. But that parameter is losing a group. It's no longer an average over the 98. See right here, these early ones contain everybody. I have it laid out more right here. So like these early groups have everybody. But as we go deeper into time, we lose people. And at the furthest reaches of time, it's only coming from the earliest treated groups. This is something for you to be thinking about. It's not about balance exactly. It's not the right. I mean, it's imbalanced in relative event time. It is imbalanced in relative event time. It's impossible to balance in relative event time unless you're willing to only work with the periods of time where everybody is present. So see, the 86 group is the 86 group has 6 years pre-treatment. We saw it right here. The 86 group does have 6 years pre-treatment. They have 6 years pre-treatment. If I'm wanting to go back further than 6 years in treatment, I cannot use the 86 group because they don't have any. They don't have anything more than -6. Okay. So this like differential timing, this differential timing stuff has all these like kind of super non-technical things that you can like not realize, which is the only way you can get long lags. The only way you can get long lags is if you are just interested in your early adopters. Okay. This right here tells you nothing, is not based on this group or that group. It's only based on my first group. That's something for you to be thinking about because I don't think that's what people think when they see something like this. When they see something like this, they see, well, the long run effect, that's what they would say. The long run effect is 180. In the 17th year, the treatment effect is 180. Well, yeah, that's true. But that's only because it's 180 for these guys. We have no idea what these guys are. Yes. When you're talking about covariates, the heterogeneity that you're talking about is different because it's not about the groups. It's not about heterogeneity across the groups. It's about heterogeneity. Yeah. In two-way fixed effects, it is, yes. In two-way fixed effects, it's a pretty big deal. All right, let me respond to that, Yinju. So Wenqing says this treatment effect is different, heterogeneous. Yes. So when you're talking about the heterogeneity with respect to covariates, you are when you're talking about the heterogeneity with respect to covariates, you are not talking about heterogeneity across groups. You're saying, are the treatment effects the same for people with high and low values of the covariates? Okay, so it's more about, do you believe that treatment effects change depending on what your covariate is? And you might think that it does, and you might think that it doesn't, but it's a strong assumption, nevertheless, to sort of just rule it out. Okay. What we're talking about here with differential timing is different. What we're talking about here with differential timing is we're saying are the treatment profiles different across the groups? And if they're different across the groups, well, first of all, if they're different across the groups, it means that the treatment was not random. If you have randomized treatment, it guarantees that the treatment effects profiles are the same for everybody. We're going to look at a paper where that's probably the only interpretation. And if you have that, if you have it where you believe that the treatment is random under differential timing, then, you know, you've got in the event study, it should be unbiased because, you know, at least in the infinitely large sample, it should be unbiased because the treatment effect profiles should be the same for everybody, because that's what randomization does. Randomization says each of the groups is the same on average. Like, yeah, each of the individual things are different, but on average, they're the same. If they're on average, they're the same, and the rollout is random, which sometimes it is. Sometimes the rollout is random. We're going to look at a paper where that's the only plausible interpretation. And sometimes it's very, very clear that it's based on selection. It's based on selection. In which case, if it's based on selection, then, you know, the only way two-way fixed effects is going to get around it is if there really is not a lot of heterogeneity. If there's not a lot of heterogeneity, then it, you know, this stuff, I mean, in fact, like if there really is not a lot of heterogeneity, it's like, it's not, none of these things are a huge deal. The thing that creates the problem is always the heterogeneity. Think back to what the Bacon decomposition was. It was weighted average heterogeneous treatment effects plus weighted average parallel trends minus dynamics in the treatment effects. Well, if the treatment effects are basically more or less the same in every period, then that won't be any bias. Okay. So all this stuff is really coming down to, you know, non-random treatment assignment. And yes, that's right, Eduardo. This is the absorbing state. That's the phrase that people use. They say the absorbing state basically means once you're treated, you stay treated. Yinji says the selection bias problem sounds pretty serious. Yep. In this case, it is serious in this case. With two-way fixed effects, it was made worse. A lot of it is coming from the long panel. So the dynamics are building and building, Yinju. So like when you have that long, because we have this long panel, we end up with lots of things that can get negatively weighted. And then secondly, we do have they never stabilize. Also, that's the other thing. Nothing ever stabilizes in this. So you can play around with the Baker.do data set, and you can play around with it in R2, and you can sort of start to use it to teach yourself, you know, why is this happening? Why is this happening? And start to kind of weaken certain things. So you could like drop years, you know, you can do lots of things and see, and try to teach yourself through simulations about why this is the case. I encourage you to do it. I've done that myself, and it really did help me a lot. If early treated group anticipate, yeah, so Donglei brings up a good point here. These kinds of things, this is where, so Donglei is describing a treatment assignment mechanism. Even though Donglei is talking about anticipation, Donglei's talking about a treatment assignment mechanism. They're choosing to get treated. This is really one of the things that you should always be a little bit concerned about, you know, is when people are sorting into the treatment based on the beliefs about what their own treatment effects are, then the organization of the dates will group together units that have different dynamics. Okay. And so selection kind of can, like, these selection problems can immediately come in and destroy a two-way fixed effects that might not some of the robust estimators. The robust estimators can still allow for certain sorting. It's changing, Robinson, but we're going to talk about that. I think the answer to that is that we're sort of looking at fossils a little bit. We're looking at papers that are published. And there's a couple of reasons for this. In fact, I would say part of it, one of them is, these papers were coming out at a time when the paradigm shifts had not fully taken place. And so some people were not really sure of the right way to present their estimates. So they knew that they had a lot of people around them that, or maybe they felt like they didn't know what to do. So they would lead with two-way fixed effects, and then they would then go in with robustness. Like we do that. I do that in my paper. Well, I don't have my Craigslist paper that just got published at Journal of Human Resources. That's what we did. Why? Because the first submission of that paper is here, was to AR, it was to QJ 2017. And in 2017, I bet I don't even have a Bacon. Yep. I don't even have a Bacon decomposition. I don't even reference Bacon. September 2017 gets rejected. We used diff and diff, and we presented two-way fixed effects. Poisson. I think it was a lot of Poisson, actually. So we did that. And we leaned really hard on falsifications. So it gets rejected. Where do we go next? Probably AR. I don't have the submission. QJ. I did that one. JP. Okay, I don't have that. So then we drop down. So we get rejected both times. I think we go to EJ. All right. I don't know where do I do these? Manuscript. Here we go. Oh yeah. So look, it goes through 6 more iterations. So now, this is now, yeah. So let's see. Do we do Bacon? Still don't do Bacon. All right. So still not doing Bacon. So that's 2019. So then what? Rejected, EJ rejected, management science rejected, AJ applied rejected, restud rejected, R&R. So we get an R&R at JHR. And when we do that is when we start changing it. So here it's like May 2019. Then we start citing Bacon. And so our solution was we end up using, at the time, we use matrix completion. We use matrix completion, which was also a thing for staggered rollout. We didn't use the diff and diffs. We switched over to matrix completion. And so it kind of like goes through this like evolution. But then in the final draft, let's see if I have it here, something like this. Well, it just came out. So basically it took forever for the issue to come out, but basically it just came out. So how do we present our results? We organized it using two-way fixed effects. So we like do the two-way fixed effects, event study, randomization inference, and then we like discussed it and we present matrix completion as an alternative. Okay, so we like present matrix completion as an alternative. We presented that. Then we did our falsification. So it's like, why did we do that? We did it because the paper kind of started in 2017, or it was first submitted in 2017. It doesn't get published till 2024 or 2023. We did it because we were trying to it was like we were on we didn't, German. We never. So I was in the group very dialed in to this new literature as it was emerging, but I had a diff and diff, under review before the new diff and diff literature. So it was like I was simultaneously working on the resubmissions with my team and learning the diff and diff as it occurred. So you watch it change, but it wasn't changing because of the referees. It was changing because of me, because I just was like needing to do, felt like I needed to do it right. So the paper like changes a lot. It changes a lot at JHR. The first time it's submitted to JHR, I don't think it has any bacon stuff. It's only in each round I would add more stuff and then have to explain it to the editor and explain it to the referee, which I don't really recommend, but I mean, I was really anxious. I didn't want to do a project like this and feel like it was wrong. So we did not get any new comments, but now you do. And then secondly, Robinson, there is actually a fair amount of diff and diff illiteracy. There is a lot, there is not nearly as much of a saturation of understanding about diff and diff. And if there's not a lot of literacy about diff and diff out there, then it can be a little chaotic about what people choose to be their preferred specification. We had, I saw presentations this year, and you would hear that. You would hear people say things like, well, we present two-way fixed effects, and then we do this one estimator of the 6. We do this one estimator, and but we don't present it as our main specification. And they would say, because the literature has not converged yet on what the preferred method is. And that's kind of a weird statement, because, it shouldn't really be that you're following the crowd. You should do it because you think it's the right thing to do, not like that kind of herding approach. But many people are really overwhelmed. They're overwhelmed by the number of options. And so you've got this, you still have this main specification stuff where people will present two-way fixed effects, maybe because amongst their constituents, their community, two-way fixed effects is still viewed as the method, which is probably going to be the case for anybody outside of econ in the workshop. But in labor economics, I would say probably, you're going to, I actually don't know. I don't really know where this is, but I don't think that is probably going to stay that way, Robinson. I think probably it's switching, because you're seeing more and more now, and you're even seeing it with Andrew's citation count. Andrew Goodman-Bacon's cites are slowing, but Callaway Santana and others is not slowing. And so what you're basically getting now is people just skipping over fixed effects entirely. They're just skipping over it entirely. Or they're doing a particular kind of graph that I'm going to show that you guys have probably seen. Interesting. When she said he went to a conference. Well, then that's a good example. It's so spotty. It's so spotty. You go to a different conference and you don't, it's just very few people, I think. But I think it is very risky. I think it is incorrect, and I think it is risky to try to write a paper now and base everything on these two-way fixed effects results. And not to mention the fact that, I put this paper down. I dropped it because I thought I didn't have parallel trends, when in fact it was just simply an anomaly coming from two-way fixed effects. Okay? It was just an anomaly coming from two-way fixed effects. You can also, though, if you feel more comfortable using Callaway Santana, you can do this same thing, though, in Callaway and Santana. Callaway Santana will also allow you Okay. It'll also allow you, because Callaway-Santana also gets all the group time average treated on the treated, it can aggregate also. And you do this by going into event study. Instead of doing ag TE simple or group, you're going to do dynamic. And so notice when we do the dynamic, look what we're getting. We're getting point estimates. They're going to be the identical to these reds. It would be interesting to overlap on top of each other, Sun and Abraham and Callaway-Santana in this graphing. In this data, they would be literally identical. Management science. Alexander says it's different at management science. Everybody on the call is going to have to take from this workshop. There's like the science, there's the science part of things, which is really what the workshop's about, is the science, which does not depend on your field. And then there's more of the rhetoric, and the rhetoric is the art of persuasion. And that depends on your audience and the amount of human capital, how that human capital is distributed in your audience before. And that differs by group. Management science is very general. It's not just econ. It goes across a huge swath of fields in a way that the Journal of Labor Economics does not. Journal of Labor Economics has as readers, editors, and referees, labor economists. Labor economists, usually very, very empirical. Okay. You go over to Restud, Review of Economic Studies, the labor economists there might be more theorists. You go over to, so, it all kind of it's a little bit haywire still, but it's changing. There is a paradigm shift going forward, because so long as everybody is rooted in causal inference and rooted in the experimental design tradition, the stuff catches up, especially as books become popular and as books kind of incorporate this stuff in. It's only a matter of time. So we get all these, and then we use GGDID to plot it. And look, it's the same thing. And these jumps, again, these jumps are coming from losing certain groups. It's coming from losing certain groups, right? This is everybody. This loses the 98 group. This loses the 98 and the 92 group. So you've got this and so what ends up happening? What ends up happening is this slope is a slope of -8. This is a slope of +8 because it's 3 groups. This slope is a +9 because we lost the lowest treatment effect group. And then this slope is a +10 because we only have the early group and its slope is 10. And you can see this if you just simply were to carry this forward. Notice that it's getting steeper. Because of the sample selection. Stacking. Stacking's another one. A lot of people seem to really like stacking for reasons I don't really understand, but there's a lot of people that really love the stacking approach. And, I think probably, Anna, we're going to continue to see some stacking, and, there's still going to be some diversity out there. And because of the amount of diversity, I guess I'll just go ahead and show you. Because of the amount of diversity, what's being done is people are just simply doing all of them. So this is code that I'm going to give you that will do all of them. So here's the 2A fixed effects. It's all screwed up. This is the, I'm not sure what this one is, but it's messed up, but it's supposed to not be messed up. It's supposed to be. That was Son and Abraham. Son and Abraham, for some reason, has got a couple of things. Anyway, so now it's doing Callaway Santana. And what people will do is they'll just do all of them while this is running. It'll do all of them. And we'll have code that'll help us do quote all of them. But let me show you an example of one of those, which we're going to talk about later. All right, so I'm going through and I'm doing all of these. But this was in the American Economic Review, and this is like the example. What everybody's doing. They just basically run 5 to 7 models. They learn how to program it so that they can put the coefficients all on top of each other. And then they show them all at the same time. Like here's one that we're going to look at. This one on ChatGPT that we're going to look at also does it. And that's becoming like pretty common. That's becoming like pretty common. So, while this is running in the background, is it important? There's no real answer to that, German. I mean, I don't think anyone is probably gonna say anything if you've got like, 3 to 5. They're not gonna say anything. Here it is. Son Abraham's messed up because I didn't do it right. So we don't fully have this figured out yet, but like you're welcome to try to make it work. But here's an example. We put them all on top of each other. We even put in here, and then the Jeff Wooldridge one looks like it's messed up. So like we've not fully figured this out yet, but nevertheless, this is like a thing people do. This is a thing people do. And so what we've done in our Craigslist paper, which we're going to talk a little bit about, what we did in our Craigslist paper was we just decided to run all of them. We aggregated to the annual level, and then we are reporting all of them. Okay. And we also do matrix completion, and then we're stopping. We're exploring some stuff, but we're not going to like, I'll explain more of that later. Okay. Yinji says, I think many people consider these estimators as fancy. Yeah. Exactly. Yeah. Yeah. It is interesting. I mean, it's taken us 2 days, and it's taken us a day and a half. How fancy really is Callaway, Santana, Son, and Abraham? If anything, two-way fixed effects is the fancy one. In many ways, it's fancy because who had any idea that that's what two-way fixed effects was doing? I mean, the code of it is not fancy, right? It's interesting what people mean by fancy. Do they mean the concept is fancy? Do they mean the code is fancy? Do they mean the mathematics underlying it is fancy? The mathematics underlying OLS is fancy. You go back to the first time you learned it. How long did it take you? That very first time. It was a long time, And how well do you understand it still? Did you know that two-way fixed effects was doing this stuff? No, nobody did. So like a lot of the regressions themselves arguably are the fancy ones. And but the way that we've framed diff and diff is cannot remotely be considered fancy because it's what? 4 averages, 3 subtractions. That's not fancy. Callaway Santana is a weighted average of 4 averages, 3 subtractions. Son and Abraham is a weighted average of 4 averages, 3 subtractions. What makes them fancy is the fact that they don't use an already treated group as a control. That can't be fancy. If you had told someone, if you took a survey and said to people, okay, do a diff and diff, calculate 4 averages and 3 subtractions, do you want to use an already treated group as a control? if people understood the instructions and people understood the question, most people would say, no, I don't want to use an already treated group as a control. So it's like nothing really is about, none of these solutions are very fancy. I go slow so that people realize that. That's why I go slow. And that's why I talk so much, is because it's not good for anyone to have this lingering feeling of that this is mysterious. It's diff and diff is not mysterious. It's not mysterious. OLS was mysterious. That OLS specification was mysterious, and nobody knew it. I know, I know. I'm supposed to be finishing. There are some books coming out. Clement and Xavier have one coming out. And if this summer I'm faculty in residence at Collegio Carlo Alberto in Italy. And my goal is to finish the mixtape. And I just have been like not doing good on it. And I'm doing too many workshops and I'm slowing me down. So I'm stuck in this equilibrium. So I gotta like figure out a way to get out of this and get the book written. But I think that you're right. I think that's how this stuff needs to spread, probably, is something that's a little more accessible, that doesn't take, you know, 48 hours of a workshop, or whatever. These things are there needs to be more pushing. I've sort of volunteered to do that, and that is probably insane, but that's what I want to do. So anyway, okay, so what we're gonna do now while y'all are talking, I'm gonna what we're gonna do is we're gonna now move into, after the break, we're gonna move into slides. We're gonna go into imputation. All right, we're gonna move into imputation, and we will talk about Borasac, and we'll talk about two-stage diff and diff. All right. And then we will look at two different papers that are kind of contemporary, so that you can is it okay if I read? When you say read, what do you mean, Lygia? If I read it? Report? If that's what you're asking, Lygia, is it okay to analyze the heterogeneity and not try to average it? I mean, that's up to you. That's up to your own research question. I mean, it's all kind of really is coming down to, what is your research question? You have to this is where it's not really the science, it's more of the rhetoric. Do you care? Do you care about the heterogeneity? You know, is it to you that the project really is about the heterogeneity? You might not average them. You might not ever do anything more than event studies. That's the other thing too. Like if you look at here in the readings of Miller, Johnson, and Waring, if you look at their paper on Medicaid, it is a ton of graphs. They do more than that too, it looks like, but yeah, here we go. So it's a ton of graphs. They will present, a summary, a diff and diff summary. Okay, they will do that, but a lot of their evidence is coming from event studies. So the question, you could ask the same question there: should I ever average into a true average? I would probably caution though, but I would say, you say true, and I know what you mean, but there is no true average. These are true also. Okay, there's ways to aggregate them. is the way I would say it. I wouldn't say it's true. I would say, how do you want to summarize them? And when these are your target parameters and you want to summarize them, you necessarily have to think about weights. And that's why we did it two different ways. We did a simple sample, a simple average, and we did a group average, where we took the simple averages per group, and then we did a simple average over the group, and you end up with a different number. They're both true. They're both true. This is the simple weighted average where everybody gets the same weight. And this is a little bit more of a complex averaging because you have a weight of 1/18 that went into this, 1/12 for this one, 1/6 for this one. And then you had a 1/3 weighting for that one. So it's like these weird weights. They're all true. Okay. But they, so you have to make a decision about which one is it that you want to report. And that's where it's like the research question drives all of this. The research question drives a lot of this, like that's what I would say. And exactly, I think Saban's right. The policy questions, and that's another way of saying it. Another way of saying is that the policy application can drive the research question, can drive the choice of the parameter, can drive the shaping of the paper. So there's not really like an answer, but I would encourage you, I would put it back on all of you and to say, what is the paper that I'm writing? What is the research question that this is about? And let that drive a lot of this. Who is my audience and who am I trying to communicate to? Even that is gonna have an effect. Like you would not really watch it. I mean, we're gonna show this, but like they do these event studies, they do all of them. We're gonna do Borsak. I skip over to Choose Hopeful, but just because we've got to move into outcome regressions, but they do that. All right. And look where it is. It's in the appendix. In this paper, it was in the main figure. Most of this paper that we're going to look at is event studies. Here, it's all event studies. Event studies, but notice it's one single estimator. Oops, Sun and Abraham. They use Sun and Abraham for theirs. Why? Because they don't matter, honestly, because there's not as big of a difference between them as people probably want to make out to be. Using the one that you really understand best is probably a good enough reason to choose that one if you had to choose one. Okay. But people are more than likely going to want to see all of them. So knowing how to present all of them is probably not the worst idea. Okay. So we got to keep going, but we're going to take an hour. We're going to take an hour lunch break, come back at 1:12 my time. We'll come back at 1:12. And then we'll finish up outcome regression. We'll cover these papers and we'll get as far into continuous treatment as we can. All right. I'll see you guys in a little bit. I was showering and shaving, and then that took a lot longer. I apologize. Okay. So here's what we're going to do. We're going to discuss these two imputation-based estimators. And let me just real quick get this over here. Okay. Gosh, I'm so sorry that has never happened before. Okay. All right. So we're going to talk about this imputation based. So if you remember what we said was that, diff and diff was two things. Number one, it was 4 averages, 3 subtractions. And number two, it was imputation. And when you ran the OLS specification with two groups, no controls, it was YIT equal A plus, B0 DI plus B1 T plus delta DI times T. And in fact, delta hat, okay, was both. They were numerically identical. You could think of delta. Well, not even think. Delta would be calculating 4 averages, 3 subtractions. It was numerically identical to that, but also it was numerically identical. It would be equal to 4 averages and 3 subtractions. And it would also use the change in the outcome for the comparison group to impute the missing counterfactual for the treatment group. It would do both. They were identical. So if you remember, you would have this, and you would say, all right, well, here's this right here, and then you would have this like event, okay, and then you would have like that would be the control group, that would be the treatment group, but the it would use that change every time. OLS would always use that change every time, okay? It would always use that change every time, and it would estimate that. And that right there was that. So it would do both of them. It would always do both of them. It would, but that would be 4 averages, 3 subtractions. It would always, so they were like always identical. Where things get a little bit different is, with covariates and all this stuff, but there was even within the world of covariates, we said, well, even within the world of covariates, there were diff and diffs that were extensions of this. 4 averages, 3 subtractions. That would be Abade's, inverse probability weighting. Imputation, that would be Heckman, Ikemura, and Todd. Outcome regression, or double robust would do both of them. No, well, there is no pre-trends, Sebastian. This is the baseline. This right here is baseline. And this is post. So in the simple 2x2, that is the baseline. Over here would be the trends. That's like, using the event study, but the actual calculation, the actual calculation is using the baseline. So what we have here though is like some subtle things here, which is that imputation though was about using the change in the outcome of the comparison group only to do the imputation. See, so when you look back at what I did, okay, I used the change from the control group to model or predict the change in the treatment group, the counterfactual change in the treatment group, because that's a Y0. So that'll be a Y0. So you're basically saying, well, here's the change in Y0. Here's the change in Y0. Under parallel trends, this will also be the change in Y0 in counterfactual. That's what it was always doing, okay? That is what all of the imputation estimators are going to do. They're not going to be finding, I mean, again, it's numerically identical. So this is like, this is just a different way of looking at the same thing. Okay. It's a different way of looking at the same thing. So just imagine though, we have not been talking about 4 averages and 3 subtractions. If you're not talking about 4 averages and 3 subtractions, you're not doing after, before differencing, right? You're just, what are you going to do instead? You're going to go, well, this is what happens to the control group. And under parallel trends, this is what's going to happen to the treatment group. That is what you're doing with imputation-based robust estimation and 2-stage diff and diff. It's just that under differential timing, it's not as straightforward as this. And that regression specification is not a possibility. Okay. Sorry. So let's look at it. So there's 2 papers. So the origin the origin of these diff and diffs are the origin of all this differential timing is Clement to Chase Martin, to Hopeful, and Kirill Borsak and Xavier Yarvil. They both come out first. Both of them were focused on, two-way fixed effects. Borsak et al. Is really, its original title is about event studies. And they both both of these papers end up identifying the problems of using the already treated group as a control. So this early on begins to pin down that it's coming from the use of the already treated as a control, but it did not have an updated version. Did not have an update. It did not have in the original papers when it was just Kirill and Xavier, they do not have a solution. They only have a diagnosis of the problem. Okay. So the paper remained in working paper form until I say here 2021. I guess that's right. So I had it stays in working paper form until 2021. And then that's when they released a new paper that had Jan Space in it. And when they brought Jan Space into it, it uses a new estimator. All right. So we're going to focus on the estimator to avoid a lot of the redundancies in the paper. And that's because this paper was coming out at the same time as others, a lot of the insights get, duplicated. They get duplicated. So I'm not going to get into all the bias to two-way fixed effects. So here we go. This is their parameter. It's the average treated on the treated. This is their notation. So this is their average treated on the treated, but they're going to talk about their treatment effects in terms of unit level treatment effects. They're going to talk about the average treated on the treated is going to be an aggregation at the unit level. All right. As opposed to groups, they're not going to be starting with these cohort ATT parameters. They're going to go even deeper. They're going to go to the firm level. They're going to say the ATT is an aggregation over the firms. All right. So standard assumptions of the two-way fixed effects. That one. Parallel trends, no anticipation, SUTVA. I should put SUTVA in here. Homogeneous treatment effects. So this is how they describe their parallel trends, right? Now, real quick, let me show you as we're doing it. Let me show you the way that I model Y0 in my Baker simulation, right? In the Baker simulation, the potential outcome Y0 is equal to an intercept right? So it's basically equal to 0.325 plus what year you are on N plus an error term. So it would be actually this right here. So it would be basically, display, it would be this number plus, that number plus this number, and that's this number. Right? More or less. Yeah, that round. So that's where that number's coming from. All right. So they assume the same thing. In their model, their parallel trends is coming from that additive model. It's at the individual level. So this is unit level parallel trends. If you look back to the parallel trends assumptions that we've been working with, they're actually slightly different. Okay. The previous parallel trends assumption that we've been working with is this expectation. Well, it's expectation Y0. treatment group post minus expectation Y0 treatment group pre minus expectation Y0 D equals 0 post minus expectation Y0 D equals 0 pre. All right. That's this is like this parallel trend assumption does not require unit level parallel trends, just average level over the group. Okay. Over the group. So it's slightly different. It's slightly different. This right here will always be true if that's true, but this could be true. This could be true and it not require that everybody has the same parallel trend. Okay. So you can have group level parallel trends and it not be the case that everybody in the group has the same trend. It just is on average. They could be canceling out, but this requires everybody to be on the same trend, plus this error term. All right, this error term. And this error term here, that's one thing to just, we're making your notes. Borsuk et al. Has a slightly different, slightly more restrictive parallel trend assumption, Y0, that holds at the unit level. Okay. And then on average, this shock here is equal to 0, which is what we have also done here. Okay. So this error term is on average 0. That's what I have, right? No anticipation means that at baseline, the unit that you're observing, their outcome is their Y0. That's another way of putting it. Just always reframe it. As you're talking about no anticipation, just remember, no anticipation is primarily not a behavioral assumption. It's a potential outcomes assumption. It just says that at the baseline, the unit, the outcome is untreated. Okay. And then they have what they call restricted causal effects. All right. And all that it means is that homogeneous treatment effects. All right. So that's how they write it. They write it out more in a little bit more of a technical term. Then they, in the paper, they critique it. I'm not going to get into this part here, but I'm going to show you this. They talk about the negative weighting that happens. They say OLS, one of the things they show is that in that Bacon, result, that the negative weighting is getting worse on the furthest lags. So that's the thing they lay out here is they say this here, that there's these negative weights and the static OLS, right, here we go. Here. So it's like the negative weighting part, I guess, that they were saying is they say, here we have two groups, group A, group B, and they are going to write out their 2A fixed effects expression. Okay, so in the period 1, all right, both of them, their outcome is based on alpha, which is this right here. Right, so it's not post-treatment, nothing has happened. It's just based on alpha. Y0 is always based on this. All right, in period 2, this group is treated. So it becomes alpha, where it was at baseline, the year effect, okay, plus the treatment effect. But nothing happened in year 2 for this group. So it's just alpha plus the year effect. In the third year, it becomes alpha plus beta 3 plus the treatment effect in that period. And for group B, it's alpha plus beta 3 plus the treatment effect in that period. And they note that the static, this is exactly, this is very similar to what Sun and Abraham were kind of also showing with this negative weighting here. They show that the negative weights are coming in the fact that the treatment effects in this year, so it's like the overall averaging that's occurring within OLS is taking all of these treatment effects, but it's placing negative weights on some of them. Okay. So you got here, like, this one, And then in the second one, it's like averaging it, but it's like reversing the weight on one of them. And that's coming from these, comparing the treatment group to an already treated group. So when you're calculating this one, you're using this group over here for the calculation. So unless they're identical, unless these are identical, meaning no dynamics, unless they're the same, that won't cancel out. So you'll end up with this, attenuation that's happening, right? Okay, so they modify the model. I'm going to ignore that, but then they note what they're going to do. All right, they're going to note what they're going to do in this method. And again, I use this quote from Imbens and Rubin. At some level, all methods for causal inference can be viewed as imputation methods. Some are more explicit than others. And here's what they say in their paper. The idea of our paper is to estimate the model of Y0 using the untreated observations and then extrapolate it to impute Y0 for the treated. Okay, so it's like, that's kind of this right here, right? Here you're using ideas to estimate the model of Y0 using the untreated observations. So here's the untreated observations, and then extrapolate it to impute it. But see, this is the untreated observations. This is the only one for which we have these are the only ones that we can use for the, well, in the original outcome regression, you use only the control group. They say something a little bit different. They're not saying we're only using the control group. They're using the untreated observations and then using those untreated observations to impute Y0 for the treated. It's like this, though. It's like you're using that to impute that missing Y0. Once you know Y0s, once you know all the Y0s that are missing, okay? Once you know all the Y0s that are missing, estimating treatment effects simply becomes a difference in Y1, Y0. You get an estimated treatment effect at the individual level, then you aggregate. That's all they're going to do. So there's 3 steps, okay? Estimate expected potential outcomes using OLS only on the untreated observations. Once you get all of those potential outcomes, then you just take the observed outcome and you subtract the imputed Y0 to get an individual treatment effect. And then you estimate the target parameters as weighted sums. You have all these individual treatment effects, then you just aggregate them. It's similar to this, only this is not, when we were using Callaway Santana and Sun and Abraham and did Chase Martin, and stacking, you do not get at the individual level. You do not get at the state level. You only get at the group level. So this is going to go even more disaggregate. But the only things you can really say anything about are the weighted averages. Anyway, so these are going to be biased at the individual level, but on average, because at the individual level, they're going to have some error parts. So, those are all going to, balance out, though, since they're on average equal to 0. In the aggregation, they're gone. So even though you are going at the individual level is slightly biased. In the aggregate, it won't be. But so how do you do it? Hold on. Oh, okay. I feel like I dropped something. So what you're going to do in this is you're going to estimate what, so, okay, well, so I guess I would just point this out then. It's as though you're going to do this. You're going to go, I haven't generated the data yet. So we'll generate the 2 data here. It's as though you're going to do this. You're going to go reg y, And I'm just gonna, reg y I dot ID I dot year if treat equals 0. That's what I have to do. I have to use whether or not a unit is treated. It's time varying. So I have to use whether or not a unit is treated, but I can only use the periods of time where I have any untreated units. Now look, I do not have any untreated units in 04 to 09. So it will not ever use periods where you have only treated units. Okay. So it will not, it will not ever do it. So when you're doing this, using only the untreated observations, it will technically not use any part of the data where everybody is treated. So it will automatically not use it. But what it's got here, now see, it's got too many, so I'm not gonna be able to see it all. But here, so what I have is panel, unit, fixed effects. I have this. The panel fixed effects, there's one right there, 0.57. I know that for every unit, okay, I know that every unit starts at their own fixed effect and then is different by the year. So it would be like 0.57475293 plus all the way down here. In 1981, 0.987. Okay. So let me show you what it's going to do. So I'm going to now go predict Y0 hat if year less than 2004. I'm going to get rid of that. So predict Y0 hat. And now I'll go list state treat Y0, Y2, Y0, Y0 hat in 1 to 10. There's Y0. There's Y0 hat. Wait, sorry. Here's Y0 hat. Let me do it better. Okay. So notice, all right, the actual outcome was a Y, is Y. In 1980, Y is the actual outcome. Y0 is the true potential outcome. Okay, which is the same thing. And then this is my prediction, 1.34181. Right? Then I get, so it's usually staying pretty close. It bounces around a little bit because of the error, but watch. So here, it's always staying the same. Then watch what happens. Now it's the years treated. All right, it's treated now. The only realized outcome is this one. That's the implicit, though, counterfactual, Y0, and I have correctly predicted it. Okay, so I correctly predicted it. So we'll say here, gen TE equals Y minus Y0. Oh, gen delta equals Y minus Y0. Gen delta hat equal Y minus Y0 hat. Oh, gen delta hat equal Y minus Y0 hat. All right. So then I'll do this. So let's go. What do we want to put in here? Firms. Yeah, I don't think I need this. I want to see ID group year treat date. Treat. Delta. Okay. These would be my coefficient plots on the pre-treatment. They're approximately 0. The true treatment in each year, 10, 20, 30, 40. My estimate, 10, 20, 30, 40. Okay. So what it's done is it's estimated the fixed effects. Since it estimated the fixed effects, it can impute the missing counterfactual for every one of the units, and it can do it. It can do it. So now we've got this, like, these individual level treatment effects. So I could do something like this. I could go sum delta hat. Right. But oh yeah. So it's like sum delta hat if year greater than equal to treat date. Maybe that'll do it. There it is. 68.33. Let's go back to this right here. 68.33. See, so it's going to be like, it's really straightforward, right? You could go, what about if you wanted to go, collapse mean delta hat by, what do we want to say? What, by year treat date? Okay, so we could say list year delta hat if treat date equal 1986. Look what it gets. The 10, the 20, the 30. The 10 gets all of them. What if I wanted to do list year, treat date, 1992? Gets all the zeros. 816, 816, it gets all of them. List year, treat, or list if treat date equal 1998. Oop. List if treat date equal 1998. Also does it. List if treat date equal 2004. There is nothing. List if treat date equal 2004. It's got a bunch of garbage. Like, so it does attempt to get these. I guess I need to, probably the actual command does not attempt these. I just wanted you to kind of see, though, that this is really simple. Okay, it's really simple. It's using parallel trends of that form to get all of the imputation, the imputed treatment effects, to get all of them. And then once you get all of them, then you can just be like sum delta hat if year greater than equal to treat date and treat date equal 1986. And you can get that average. There it is right there, 95. 95. Get 1992, 52, 52. You could go, you can get all of them. 21, 21. It's incredible how a lot of the fixes are not very complex. They're not as complicated as the papers themselves are. What it requires to prove the, to actually prove these things is a little bit more involved, but the actual methodology itself is very straightforward. Okay. So, so that's it. Estimating the expected potential outcomes using OLS means just using the Y0 model. You have to use the Y0 parallel trends model. Okay. So using the Y0 parallel trends model, if you believe that covariates are part of it, you got to put the covariates in, whatever. But that's the basic idea. Once you get it, then it's just a matter of imputing, and then it's a matter of calculating the differences. And it's all does this for you with the software, but that's the idea. Okay. So they compare it to its performance. And I wanted to show you a little bit about one of the ways that these methods will differ from each other. Okay. One of the ways that these methods differ. So we're going to compare it in the coefficient lags, right? So this is like the post-treatment lags. So this would be essentially here, 0, 1, 2, 3, 4, 5, right? So that's 0, 1, 2, 3, 4, 5. Yeah, exactly. So Eduardo, I'll put up here. So Eduardo asks, the untreated units are never treated or not yet? Exactly, yeah. You're using everybody. You could limit it. You could limit it. I mean, technically, you could get in there yourself, program this up yourself and say, I'm only going to use one. If you wanted to only use the never treated, there's probably a way to do it if I had more time to think about it, but but you'd probably have to manually do something. You could, yeah, Pablo, you very well could. Absolutely. You would be imputing the Y zeros. I haven't thought about this, Pablo. So you would be imputing Y zeros under a parallel trends assumption, and then that would let you get Y zeros. If your treatment parameter is all about that missing Y0, then you could use your continuous dose, all right, at any period and just compare it to that Y0. Lots of times though, Pablo, so you could do that. You could do that. And I don't have another response than that. So I need to think about a little bit about if there's more involved in the continuous. Maybe this afternoon when we look at it a little bit, we can see. But in principle, yes, Pablo. In principle, if this is the correct model of your potential outcome, right? Then it's got nothing to do with the dosage or anything. It's just saying this is what Y0 should have been. Okay, at all periods of time. Then a treatment happens and then it takes on a particular dose. All right. So you could do this. Now, the only way you could do it is if you had units that were not treated that you have some untreated units in every period. Or, or that's what it would require. And lots of times with continuous, Pablo, with continuous diff and diffs, there's never a period where you have a dose of 0. So that's part of the issue here is that, you need to have doses of 0 for someone at every period in order to get those fixed effects. And if you're starting out with a continuous diff and diff, if you're starting out in a continuous diff and diff, and every single period someone has a dosage that is not 0, then that won't work because you can't impute the missing Y zeros unless you actually have dosages of 0 to work with. And lots of times you don't have that. So like in our abortion paper, where we looked at the effect of abortion clinic closures, I didn't mention this, but I have a continuous diff and diff paper. When we were working in that project, it was the effect that the clinic closures had on driving distance to the nearest abortion clinic. Okay. And in that project, you always had to drive to you never were living inside of an abortion clinic, which would mean there was no driving distance. You always had to drive some distance. Okay. So you didn't really have as much of this. Well, that might not be exactly true, but I think the way it was actually calculated, you had to calculate the distance for every county to an actual physical address using the centroid of the county. So I think we always did have a non-zero driving distance mechanically. But yes, It's not exactly like that. There could be an inability to do it, but in principle you could. Principle you could. Is it similar to synthetic control? Yes, similar. Synthetic control doesn't use a parallel trends equation like that, but without getting into too much of detail, yeah, it's pretty similar. Both of them are imputing missing counterfactuals using only the control group. Synthetic control is doing a kind of distance minimization, but yeah, it's pretty similar. And it's doing the differential timing, which it's not doing. Okay. So look at this performance they do of these Monte Carlos, and I want to show you a little bit and help explain why this performs differently. Okay. So in this table, they're going to compare how their method called imputation, robust efficient imputation estimator, how it compares with DeChase Martin and Sun and Abraham, which are all very similar. And you're going to see that the bias terms are not very different. So like the baseline simulation, they're not even going to look at the bias. They're going to look at the bias over here when they violate no anticipation, which I'll explain more in a minute. But here they're just going to look at the standard errors. All right. So in the baseline, all right, because of the modeling of assuming they assume a particular structure of the data, they assume that the data is homoscedastic, and they're gonna relax the homoscedasticity in just a minute, but they're gonna first look at the homoscedastic situation. They're all pretty similar. Okay, they're all pretty similar to one another. But the variance is slightly larger in the other methods. This one, on average, has a smaller confidence interval. Okay, for every period. So here we have the variance here, 0.009 versus 0.014. Notice how it's a little bit different. They bounce around a little bit, but this one in the long run, under homoscedasticity, in the long run, Sun and Abraham has slightly larger confidence intervals. Okay. So then they put in more pre-treatment data. And I want you to notice what happens here when they put in more pre-treatment data. Numbers stay the exact same. When you put in more pre-treatment data, the Chase Martin and Sun and Abraham estimates of their coefficients do not change. See that? They're always the same. And that is because they are, for average, 3 subtraction methods. They use a single baseline. For every one of these coefficients, they use a single baseline. It's the t minus 1. So for this calculation, they used t minus 1. And for that calculation, they used t minus 1. They do not take all these other new pre-treatment years for this calculation because it's just simply average, 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 do the differencing. This one's different. As you put in more pre-treatment years, notice that the variance, the standard errors get smaller. The standard errors get smaller every single time. And the reason is because all of these coefficients in the robust imputation estimator, they're using all of the they're using all the data for the imputation. They're using all the data for the imputation. So like when we were over here doing this, okay, when we estimated this, these coefficients, they were coming from a regression. They were coming from a regression that used all of these data. I put in more years of data. I am increasing my sample size. As I increase my sample size, I am getting more power. And as I have more power, I can get more precise estimates of all of the fixed effects. And so simply by putting in more data in this outcome regression model, this outcome regression model doesn't just use the baseline for any of its calculations. It's using all of the data. It's using all the data to get all of these fixed effects. Once it gets all these fixed effects, it imputes. You put in more data, it will have more power. Has more power, the sampling variance goes down. The sampling variance goes down, the standard errors legitimately fall. You get more precise estimates. So that's one of the things to be thinking about. One of the things to be thinking about is that these can be more precise with more data in a way that is irrelevant with these, okay, with these event studies. But how big of a difference is this? That's a different question. How big? It might not be huge. It might not be enough to really make much of a difference, but it will technically, by putting in more pre-periods, it'll shrink those standard errors without having an effect on those, okay? If we now change our homoscedasticity assumption, it will cause the standard errors to rise. It's doing it for the others too, though, okay? And then we add in these AR1. They kind of experiment a lot with a lot of these residuals. And here, these AR1 residuals, they're having an effect. You know, they look at it, it's not really having a big effect. But then we have this violation of no anticipation. Well, the effect of no anticipation violations on the bias of this estimator is smaller because it uses more periods of time. It's using more periods of time where it does not have anticipation violations, but you know, it can still make a difference. It might not be huge, but it can make a little bit of a difference. Okay. So let me see what here. So Wang says, when I use CSDID at individual level, well, you shouldn't even be able to use it. You cannot estimate an individual treatment effect with Callaway-Santana. You can only estimate the group stuff. So the only thing that you can get with Callaway-Santana is the group time average treatment on the treated. You'll only end up with these numbers. Okay, that's the only thing you can get in every period. And when we did this, well, yeah, it's gonna go through it. It can't do it for every period. So like with Baker, it's not gonna be able to do it. See, it can't do those. And it can't do those because Callaway-Santana requires an untreated unit at that period of time. So if there's some things it won't do, it's because in that period of time, there is either there is no comparison group. Okay. So like here's an example. It's got no coefficients in that period. Why? Because the O4 group has no comparison group. So since the O4 group has no comparison group, it can't do it. And from 04 to 09 for that group, it also can't do that. So there will be so all that means if CSDID is spitting out, no coefficients in every period, it means that you don't have any untreated units in that for that at all. You don't have any untreated units. So if it's spitting that out, it's either a coding syntax mistake or you really don't have any untreated units in that period. Okay. So, I'm going to now talk about, so I could look at like this paper. I guess I could just briefly review this paper by Michael Clemens or is it Clemens and Strain? They implemented, and this is not uncommon. You'll see people do their paper and they'll only use one of the methods. They'll only use one of the methods. They'll pick one that for some reason they'll use one. Which is fine. They might be willing to assume the unit level parallel trends. And, they've got a lot more data. They want to exploit the power parts of it. So that might be a reason to do it. So you go Clemens Strain, they use the BJS imputation estimator to estimate the effect of the minimum wage on employment, right? Post Great Recession. Okay. Now, BJS is not gonna, it does not have a base period, okay? It does not have a base period at all. So it's gonna impute, when you do BJS, all right, when you do BJS and you're doing all of this, okay? So you're gonna go like this. You're gonna run this. Okay, while it's running in the background, you're gonna get all those fixed effects, okay? Once you get all of those fixed effects from that regression, you're going to use all those coefficients to then get Y0 hat, okay? So I'm going to then do that, get my Y hat, get my delta hat, and then I'll collapse it. I'll take the collapsing it by, maybe I want to make an event study. All right, maybe I want to make an event study. So I'll collapse it. All right. So if I want to get an event study, I've got to create a gem time till equal year minus treat date. Right. So now what I've got to do is I'll have I could sort time till, I could go by sort treat date, sort time till. Sort treat date time till. Okay. So then what I've got is I've got it by treatment group, and I've got all these estimated treatment effects. You can see that they're right. Okay. But let's say that I want to do what I was doing here and create an event study plot. I want to create that thing. Then what I've got to do to create this, all right, is I've got to collapse it. I've got to average it by, I've got to go, collapse mean delta hat by time till. Okay. And notice it'll do it. But look what it does though. It gives you coefficients. It gives you an event study coefficients for every period. Notice that it even gives me one for -1. There is no baseline, is what my point is. There's no baseline in Borsak, Yarville, and space. There's no baseline. You have correctly imputed everything. You've imputed everything using those fixed effects. So since you have a year fixed effect and you have a panel fixed effect, you can go, you'll be able to go start at some baseline. So in 1980, everybody's Y0 is based on their fixed effect. And everything else is based on fixed effect plus year fixed effect. That's all it ever is. So technically you have all this. Okay. You have all that right there, which means you have all this. You're not missing like a baseline. Whereas when we are working with Callaway and Santana, Sun and Abraham, there's a baseline. Two-way fixed effects, there's a baseline. There'll be some omitted category, some omitted group. Okay. Doesn't happen here. So when you're looking at these BJS plots, the thing you have to remember is that they will not have a base period. They will have estimates of every single relative time period. It's imputing the counterfactuals, so it can get the average treatment on the treated for every period. So you're going to see this lots of times. See how triangle has confidence intervals? Everywhere there's a triangle, it has a confidence interval. But if you get really close, circle, Sun and Abraham, no confidence intervals. Square, two-way fixed effects, no confidence intervals. Callaway Santana does, but like one of, it's because it's doing that rolling thing it does. So it will have one. The Chase Martin, no confidence intervals. So 1, 2, 3 has no confidence interval. But Borisac and Callaway Santana are having it because, Callaway Santana is just rolling its baseline around. But the Borisac at all is not. It's just imputing it. Now it's got a way of getting its own standard errors, which we, have skipped over, but other than that, that's how it's doing. So here's what they did. So this is, they're wanting to know the effect of increases in the minimum wage on employment using the post-Great Recession minimum wage increases. The post-Great Recession minimum wage increases were huge. Relative to the historic ones, they were like bigger than it had ever been, starting at a much higher baseline too. So they were much higher than they had previously been because they paused it. Basically, all these cities and states paused their increasing of the minimum wage during the Great Recession. And when it came back on, they just came back pretty fierce. So here we have figure displays coefficients obtained using the imputation estimator proposed by BJS. We code the first treatment year is the year in which a state's first blah, blah, blah. Okay, so they're going to do low skill young. So they basically, and then they put in controls. So when they put in controls, they're able to get like a little bit more significance on it. And then they kind of like explore some heterogeneity with it. So like if these were really large states that had really big increases, the effects were really large. They were pretty small. They didn't really have an effect. So the only place they're finding effects of the minimum wage is on large increasers. The small increasers, it doesn't really do anything, but the big ones it does. So you're watching people, and notice at the baseline, everybody's got a point estimate, everybody's got a confidence interval. Okay. So they end up, using it. That's a new paper. They're using this paper, using this method in this paper in order to, and they only do BJS. They're, focused on BJS in it. Okay. So what I want to do now is take a 15-minute break. We'll come back in 15, and I apologize. We'll come back in 15. And from then, we're going to see how far we can get into this two-stage diff and diff. We'll discuss two papers that do this now, so you can kind of see a little bit of some choices people are making. And then we'll go into continuous treatment. So we'll come back in 15 minutes. Believe that it's time. So while I'm just kind of I'm going to answer this. When she said, do you have the simulation do file? Simulation? Is it the Baker? The Baker do file is here. The I was using baker.do, and baker.do is in lab under solutions. Baker.do here is where I'm generating these data, but the the actual, okay, good. So let's cover one more estimator, and then we're gonna kind of bring it together into a we're gonna bring it together for Katie for a kind of like a practical discussion. So John Gardner had a paper also very similar to this paper was very similar to the imputation estimator. Technically came out before the imputation estimator update to that original article, but it's the last of the early papers that has not been published. So he's got this paper, he calls it two-stage diff and diff. So there's a couple of things I like about it. There's three things in the paper. We're just going to kind of probably focus on the estimator just to save time. But one of the things he does in it, if you're really interested in trying to connect the econometrics of why strict exogeneity requires constant treatment effects, he has a discussion of it in there. And I have it in the notes here, but I'm not going to go through it. Every time I teach it, I feel like I lose half the audience. So I'm not going to teach it, but it's in here where he discusses that strict exogeneity does require constant treatment effects. You know, it assumes constant treatment effects. He's not the only one that has said that, but you can at least sort of see the proof of it if you're wanting to. But he's also going to introduce his two-stage diff and diff. Okay. And he's going to show this method. It's an outcome, it's an imputation estimator, an outcome regression method. And his approach is the same thing as his solution is basically the same thing in a way as what the authors did in Borisov et al. He's going to estimate the panel fixed effects. He's going to, and I'm going to go ahead and have this be doing in the background. So I have this run in the background. It takes a second. So here, so I'm going to do that. Okay, so while it's doing that, and he's going to get those panel fixed effects, and he's going to get the time fixed effects, and then he's going to do something called residualize. He's going to delete from the outcome the fixed effects. And I'll show in a second what he does while I'll do this manually together. Okay. And then he's going to run normal analysis. Now he connects that up. He connects up here. So he's going to connect the failure of the two-way fixed effects model. He's going to connect that up to his solution. So he's going to argue, he's not going to argue, he's going to show that that original two-way fixed effects model had been misspecified. It had been misspecified. And because it had been misspecified, if there's heterogeneous treatment effects, it's misspecified because it doesn't model those treatment effects. And what happens is that this misspecified diff and diff regression model projects the heterogeneous treatment effects onto the group and the period fixed effects. It basically misplaces the heterogeneous treatment effects. It misplaces them. Rather than putting those heterogeneous treatment effects inside the dummy, it puts them inside the fixed effects themselves, and they get all, and you end up with this complex error term that ends up getting correlated with the error with the fixed effects themselves. So what he's going to do is he's going to go in two stages. Actually, very similar to what I did. He's going to go in two stages. He's going to go step one, estimate the fixed effects. Step two, it could really be three stages, but step one, estimate the fixed effects using only the D equals 0 observations, not the control group, D equals 0. Any unit of time where something is not treated, you're observing their Y0. So he's going to be using anybody that's untreated, all right, in any period. Run that regression, get those fixed effects. This feels like multiple steps, actually. He calls it 2 steps, but this feels like there's a second step in here. But he's going to estimate it, get the coefficients, which I just did, right? So basically, I just estimated panel firm fixed effects, year fixed effects, using only the untreated units, untreated unit periods. Okay, so I get all of them. But rather than use these to impute, he's going to do something different. He is going to subtract out from the outcome. He's going to subtract from the outcome the fixed effects. He's going to residualize them. And then he's going to get a transformed outcome where the fixed effects have been removed. Now, if you go back to this model here, if you're assuming this, if you got these, okay, if you got those right there, then he's going to then take your outcome and he's just going to subtract the alpha, subtract the year, okay? Now, why does that matter? Because of this. All right, so here's here's going to be like his regression equation. All right, so we know that like you have these group time average treatment on the treated kind of effects here. So this right here, this expression, this is the group time average treated on the treated, but it's going to be expressed in like more traditional econometric notation because it's going to use these beta coefficients. But that's basically average. This is a treatment effect for each group in each time period, right? So he's going to say, all right, under parallel trends, the average outcomes is just going to follow this equation. Under parallel trends, the mean outcomes are going to be the firm fixed effect plus time fixed effect plus, if you're treated, the average treatment effect in that period, right? Okay. And where beta is just treatment effects. So we're getting these like, if you're treated in a period, beta on average is equal to Y1 minus Y0 for that group in that period. Right? So we rewrite it, we rewrite this, and we know that this term right here is equal to this. So we're going to rewrite it, okay? And we get our fixed effects, we get our average beta here, but we've got this heterogeneity. We've got this heterogeneity where this average of this beta, okay, is equal to the beta minus, any heterogeneity within that treatment effect. So the problem is just what happens is that the outcome, because of this heterogeneous treatment effects, you've got both like this effect when you do this mechanically. When you do this mechanically, you end up with the heterogeneity, the treatment effects differing for groups and at different times. I think so. Yeah, I think that must be. You're right. That's missing a plus sign. I'll dig up in Gardner's and just double check, but I believe that this is missing a plus sign. Yeah. Let me just double check. Yeah, plus. All right. So you end up with this plus that. All right. So let me just. I'll do it later. You end up with this plus that. So that should be a plus right there. Right. So using this measure, this is an error term. So it's in the difficulty of the regression approach above, except in special cases, the error term, this varies at the group period level. It is not on average. This whole thing is not on average going to be 0. And because of this heterogeneous treatment effects. So as a result, this whole thing ends up in the error term. And so if on average this is not equal to 0, if it varies also with the fixed effects, okay, if it varies with the fixed effects, then these fixed effects end up being correlated with these values, and you don't end up being able to recover just this. This is what you care about. This right here would be the average treated on the treated for that treatment group. And it's correlated with this, and then this ends up being correlated with the fixed effects. Okay. All right. So I want to skip to what he's going to do. So what he's going to do is, first stage, he's going to run this regression off of the d equals 0 only, get these coefficients, which is what I've done here. Right. So I've done this first stage, run this regression, treat equals 0. Get my panel fixed effects, that would be these, and then get my year fixed effects. And that would be these. All right, so I've got all these fixed effects. Second stage, what I'm going to do is I'm going to delete those fixed effects. Since I have used periods of time where nothing is treated, then that's a 0. That's a 0. So I'm able to get unbiased estimate of these fixed effects. In the post-treatment period, the problem is the fixed effects themselves end up being biased in the post-treatment period because they're correlated. The fixed effects are correlated with this term right here. They're correlated with the fact that in different periods, in different groups, the treatment effects are different. It's like, weirdly enough, the heterogeneity of the numbers themselves are tangled up with these fixed effects. You cannot get unbiased estimates of the fixed effects because the unbiased estimates of the fixed effects they end up not being separated out. So you're going to just use the periods of time where d equals 0. That goes away. That goes away. You get these, okay? No longer connected. So what you're going to do is you're going to take your real outcome and you're going to subtract out your coefficients and get this residualized, thing. But I don't know off the top of my head how to exactly do it in front of y'all. I don't know, because if I type in predict, what could I do? Oh, I think I could do this. Predict. So I'm gonna drop if year greater than 2003, just so I don't run into any trouble. So I think I could go. So since this right here, the sum of those two is Y0, I think I could go. Yeah, it is basically an extension of Frischwell level. It is kind of like an extension a little bit of Frischwell level, but I can basically go predict Y hat. Do predict Y hat because I've got the fixed effects. Wait, drop Y hat. So I'm going to say predict Y0 hat. Y0 is the sum of these two. Like if you look back at, it's easier because I wrote it better here. See, Y0 is just those two. It's just the sum of those fixed effects. So what we're going to do, yeah, there it is. So we're just going to get Y0s here. That's all these are. Then I'm going to get either, I can think of it as those two, or I could just think of that as Y0 hat. and you're going to residualize. So I'm going to say this is equal to, think that this should work. All right, so gen new y equal, we'll call it resid y, equal to y minus y0 hat, because I had done y. Yeah, so I'm going to do that. All right, so now I have this new residualized. And now, if I'm not mistaken, if doing this, I haven't done this in front of people before, but I believe now I run a regression just on the treatment indicator. Reg, resid, y hat onto treat. Yep, there it is, 68.3. So 68.3, if you remember, 68.3 was what? The simple ATT. So what it did was, and I've got this standard error associated with it. Now, this is incorrect. This is an incorrect standard error. And the reason why it's in an incorrect standard error is because this standard error does not have the correct degrees of freedom here. See, it does not know that I just did, like, let's look. How many fixed effects did I estimate? 1,000. So see, that standard error has the wrong degrees of freedom correction in it. Degrees of freedom. Here we go. So it thinks it only has one, when in fact there's 1,000, 1,003. So you can't do it manually. Like that's, it's kind of like the same way. It's the same way you're not supposed to do two-stage least squares in 2 stages. You're supposed to let packages do it. Same thing here. But putting that aside, by the way, Kitty, that's why it works. So you residualize the outcome by deleting out the fixed effects, because the fixed effects are the problem. Ironically enough, in the differential timing setup, the fixed effects are the problem. They're the ones that are biased. They're biased because they're correlated with the error term. And the reason they're correlated with the error term is because they contain because they're correlated with this new composite error term, because the fixed effects, the treatment effects differ by group, and they differ by time period. And in the post-treatment period, the Y is the sum of all of these, and these are correlated with that. So you have to residualize them. Once you residualize, it ends up, as we saw, it ends up being fine. Okay? So, but the standard errors are wrong. Because the dependent variable uses estimates obtained from a first stage, and there was a huge number, in our case, of the fixed effects that were estimated that's not incorporated in. So what you can do, though, is he shows his estimator, his two-stage diff and diff estimator, he shows the asymptotic distribution of the second stage, meaning we need to get the correct variance under this, large sample situation. We can use this joint generalized methods of moments procedure, and then simultaneously do the first stage and simultaneously do the second stage. And then we will be guaranteed to get the correct standard errors. Okay. Let me see if I can't do this real quick in front of you. All right. So the Gardner command is like this. All right. So we're going to do Y. First stage, I.year, I.ID. Second stage, hold on. Help D82S. I think that let me see. Okay, that's what I need to do. So I go I.treat ID. Let's see how long it takes. So we had a standard error of 0.403. It's going to take a little bit because of how large the data set is and how many fixed effects that it's getting. So all of these are really probably going to need under the hood to do some kind of high dimensional fixed effects kind of package. You could do this manually with GMM, but see here, coefficients exactly the same, 68.3, 2906, 68.3, 2906, but my standard error is way too small, 0.403. It should be 2.5 times larger. And so, it's not really changing my confidence intervals a ton because the Z statistic is still massive. But you can see here that it is actually manually precisely what I took us through. It's exactly what I took us through. And you just have to get the standard errors correct. You could use literally GMM. In fact, I think I might even have an old Substack where I did that. So if I just did Gardner. It's DIDI2S. No, I guess not. So I don't have the GMM command myself. Huh, what is this? So, but here I did attempt it. So DIDI2S. But you can do all this stuff. You can even use weights in here. There's probably a lot more that you could do. I bet you could even, well, you can put in covariates. You're gonna have to make some assumptions, but yeah. Okay. Anyway, so that's how you do it. It's really straightforward. Okay. These are all really straightforward. Those two methods are not terribly different from each other. Okay. But what I want to do now is I want to discuss real briefly a couple of papers that have come out recently that use staggered adoption, just so you can kind of see it. One's a paper that came out in the American Economic Review last year or 2022. Another is is a paper that's a working paper, right? Okay. So it's Mark Zuckerberg went before Congress, said there was no evidence of social media causing any mental health problems amongst poor young people. Unclear what he meant. Probably meant there's no randomized control trials. Probably means there's no experimental evidence. But also, frankly, most of the evidence that we have about any negative effects of social media on young people is probably not causal. It's a lot of it's correlational, anecdotal, journalistic, parental observations, deductions from psychologists, but there's not really been any RCTs because it's very hard to do an RCT like that, especially if there's already some evidence, correlational even, that it's harmful. It's not going to be possible to do an RCT. So get it past IRB. So quasi-experimental evidence is really all that we really have. And right now we're so social media saturated that, it's really hard to model the counterfactual with anybody. Who would you use now as a control group in a non-randomized trial? Who would you use as a control group? Someone who literally never is on social media. It's hard to find somebody like that now. And probably anyone like that might be very, very different on observables and unobservables from people that are on social media. So there's a lot of great things about this paper, but one of the great things about the paper is that the counterfactual is more plausibly a situation where there is no social media. They're going to use the rollout of Facebook. If you've not seen this paper, they take advantage of a clever quirk in Facebook where originally Facebook was not called Facebook. It was called the Facebook. and they targeted different universities from 2004 to 2006. So if you've seen Social Network by Aaron Sorkin, you've seen them discuss how they were targeting different schools at different points in time. Now, Facebook does not share the full rollout. They share a little bit, but they do not share everything about where everything went. But they do this cool thing. They use the Wayback Machine. And they do this. And they went month by month, or they went, day by day through every single one of these pictures. And look what's on the front page of the Facebook. The name of the school, right? First it says Harvard. Then it says Columbia, Stanford, Yale. And they just go snapshot through snapshot. And they realize they're updating the front page to try to build excitement, I guess, but they're showing that they know the full rollout. They figured out the full rollout of Facebook by just going through every single picture. And eventually they can start to see who gets added and when. Okay. So what they're going to do is they recover. It's really brilliant, and this just kind of goes to show you, and this is what we did. And I mean, I did not get our Craigslist paper was before this paper. And so I wasn't, I wish I had thought of this though. I did not think of this. But they get the idea also, to do this too. They get the history of Facebook. They then link these dates to a long-running health survey of college students before and after using this. They get very lucky in being able to do it. And then once they get both of them, then it's a matter of just doing, the work. These were definitely two of the more, the fact that they found the rollout on the Wayback Machine is huge. And the fact that they were able to link it to a long-running health survey of college students is also huge, right? So if we think back to my metaphor from day one of what constitutes good evidence in a diff and diff, I said there were 5 things: bite, main results, falsifications, event studies, mechanism, right? So it's like, this shows, this in this case would be, bite would mean when Facebook shows up at a college campus, do you find people spending more time online? Do you see them get on Facebook? That would be like actual data from Facebook on, do we get how many students get on Facebook, right? When it shows up at Dartmouth, when it shows up at, University of Texas, how many people actually get on the web, how many people enroll? They don't know. Okay. So they cannot get this kind of data on Byte because you would need data from Facebook. And so they don't have that. They really just have to rely on anecdote and other documented statements about how popular Facebook became. But there had technically been other social media platforms. MySpace and Friendster, for instance, existed. But the thing is, we do know that neither of these survive Facebook's expansion. Something about Facebook, even though they were very similar to both of these, something about Facebook is clearly very different than what appears to be platforms, because these basically get destroyed. These had been worth like $1 billion. Friendster had an offer of $1 billion from like Robert Murdoch or something like that. They turned it down, and that company is gone. MySpace still exists, but I believe is nothing like it used to be. They both get decimated. by Facebook, and obviously Facebook's one of the largest companies in the world. So there is no evidence of bite except for like, a widespread agreement that there is bite there. I want to just pause for a minute. The only reason they probably don't need bite, evidence of bite, is because everybody already believes there's a bite. If you're in a situation where people do not already believe you, you won't be given probably the same chance. This is at the American Economic Review. So it had to be basically that referees and the editor really did believe that when Facebook showed up at schools, students got on Facebook. But, I had to, in my paper on Craigslist, I had to show a lot of evidence of bite. I had to show a lot of evidence on bite, the one that was just published. And we had to do that in lots of different ways. And we did. We had evidence of bite. So you got to show, depending, the more obscure, the less well-known something is, the more you're going to have to show evidence of bite. Okay. So that's one thing. Then they're going to show their main results. They're going to show very strong evidence, and they're going to have very strong claims. Very strong claims using the rich survey data and the questions. They're going to turn all their questions into Z-scores so that you can interpret everything in the same way. But they have very strong results that they're like going to claim are causal. Their falsifications, remember, have to do with post-treatment placebos. They have none. They do not have anything that they can link to their Facebook data, right? They've got this Facebook data. They do not link it with falsifications that are otherwise, predictors of mental health problems. They don't do it. You could do it. We could do it. You could write a paper. Getting this Facebook data is not hard. It would take like a couple of hours probably. You could do it. All right. And then you could do your own study. No, because this is a time when Facebook is just a startup. So Facebook and stock price doesn't vary by school. So, this is all way before Facebook goes public. This is like when Facebook is literally a handful of employees. So there is there's nothing like that you could do. So it's not yet a publicly traded company. And it's also not generating any revenue either. It's not even using the ad model. So right now they're just going off of, like internal funding by, each other. Because it's not a really complicated, I don't know. So they can't do that. But you could look at things like if you had a data set, like you could do this, for instance. You could go to IPUMS, to the American Time Use Survey. The American Time Use Survey is the American Time Use Survey is a time use diary, and it has data here from 2003 forward. You've got data, and you've got like how much time they spend on a computer. So you got the activity. You can like look in here somewhere and like try to figure it out. Problem is that here, if you have geographic, the county, the MSA name. So you might be able to link a college student. You could potentially do this, and so that would be kind of interesting. That might be a way to do it. Get something like, is a person probably enrolled at Dartmouth? Are they in college? But not always is it going to work. So you'd have to get like, it may or may not work. If you can already sort of see because you don't know, you might know that they are a student. Maybe there's something there that says they're enrolled, work status. Maybe it says that they're a college student somewhere. But even then, it's going to get like pretty thin because you're going to, these data sets, those ATUS, they're nationally representative. I don't think they're representative at that level, so you'd be working with probably very few observations at the like county college level year, and you'd only have year. Whereas they, although maybe you have survey date, maybe survey date is in here somewhere. Actually, so maybe you could do this. Actually, now that I'm sitting here doing all this stuff, I'm wondering if you could do it. So maybe you could do it. That would be kind of cool. So if you could look at the effect of the rollout and you did have enough data and it wasn't super noisy and you knew the exact date of the survey, well, then you could like use the within year variation. That would be crazy. Maybe that's a project for one of y'all to do. So, and get effects of Facebook on time use. Are they substituting out of certain kinds of activities? Okay. Because I bet you studying is in here. Ah. So they're enrolled. They're enrolled. Oh man, there's a lot of stuff you could do. You could do a triple diff because they only rolls out to enrolled college students. So if you live in that county, but you are not enrolled as a college student, you cannot get on. You cannot get on because the only way that you could become a part of the Facebook was if you had a UC Davis email address. And you had to have it after that. But before that, you couldn't have it. There's probably a way to do it. Some of y'all are now going to write this paper, but you could do it. That would probably be pretty crazy. That's not too terribly hard to do. So this is the great thing. Like you could look at the effect of Facebook on, on what people are doing with their time. All right. But they don't. They have no evidence of bite. Okay. Falsifications. They have no falsification in it. You would need to find stuff that are highly predictive of mental health, but which have nothing to do with social media. Okay. To do it, they don't do it. And it's in AER. And then, but what do they have? They have event studies. And I suspect that this one event study graph is very, very responsible for why this paper gets published. That and the fact that it is a very important policy question. Because arguably social media is probably like this period of time's like smoking question. Does smoking cause lung cancer? Does social media cause these things, or is it all ridiculous and it's spurious? It's the same kind of thing. Because if it doesn't cause it, some people think it does and some people think it doesn't. And so, trying to get at that is very hard without experimental evidence. There will never be experimental evidence, probably, but there could be quasi-experimental, and to use the rollout as a way to do it. So they have this very compelling event study plot. They're studying a very important question. So that's one thing. It's a very important question, never been answered before. Okay. Never been answered before. You got this statement by Zuckerberg saying nobody's ever done it. So definitely back then, nobody did it. And you have great data. You have good questions, great data, and a good design, and you can publish in the best journals in the world. That's it. That's kind of the big takeaway. If it's a very, very important question that everybody cares about, and you have very good data, and you have an excellent design, and diff and diff is considered an excellent design, you can publish in the best outlets. It is considered to be a major scientific discovery, what they did in this paper. And then you have mechanism, and the mechanism part is very weak, but you'll see what you think. So anyway, these are what I think are some strengths of the paper for you to be thinking about. It's an important question, excellent research design. The data collection is meticulous, and the data visualization, I think, is very compelling, right? So this, though, going back to something that I think Winchen had said, or that someone else had said earlier, their main results are two-way fixed effects, right? They're going to estimate this two-way fixed effects model. And I asked them, why'd you do this? Why did you estimate this model as your main effect if you are eventually going to do all this robust diff and diff stuff? And their answer was pretty interesting. They basically said because they didn't want to confuse readers. So they were willing to present this bias estimator solely because they didn't want to confuse a lot of readers, right? So their focus, though, is going to be on beta. They're going to put in, period. They're going to put in two-way fixed effects, and then they're going to put in a bunch of controls, right? So they use the Wayback Machine, like I said, the rollout. So they went through 3 years, daily screenshots, Wayback Machine. First time Agnes Scott or Covenant appears on the front page. The authors marked that as the date when the school got Facebook. But they've got to link this with longitudinal data by school. That's the thing you have to remember. The only way this works is if they can now get college level before and after mental health data. They've got to get longitudinal data on mental health with mental health outcomes that are connected to a college, that they have to know where a student went to college. Now that is going to be hard to do because that is not going to be publicly available. So they find one of the oldest and longest running repeated cross-section surveys of college students. They don't address any of this compositional change stuff, by the way. So they could have problems with this compositional change that we talked about on day 2. It could be in here, but they do not look at that. It's a repeated cross-section. Here's what they say. Our second main data source consists of more than 430,000 responses to the NCHA survey administered to college students on a semi-annual basis by the American College Health Association. The NCHA survey was developed in 1998 by a team of college health professionals with the purpose of obtaining information from college students about their mental and physical health. It inquires about demographics, physical health, mental health, alcohol, drug use, sexual behaviors, perceptions of these behaviors. Okay? Does all those. But it does not include any questions on social media. And it wouldn't if Facebook is really the first major social media platform. If before Facebook, social media was pretty inconsequential in people's lives, then there's no reason the survey would have ever been asking about something like that. It's like, it would be like surveys are probably not asking questions right now about VR helmets, even though the Vision Pro by Apple might be about to bring in a huge change, or they're not asking questions about using ChatGPT, even though ChatGPT, when it rolled out, led to about 100 million people within a month being on OpenAI. But prior to ChatGPT, nobody was using chatbots for anything. So, you're going to have these problems. You're going to have these problems on Byte with something that is a first mover. It's something for you to be thinking about, okay? Because by definition, it's a first mover. So you're gonna have to think about, what even would be the evidence of Byte that would be in any reasonable data set that you could link to your diff and diff, okay? So what do? They contact the ACHA. Moving on from Byte, they contact the ACHA and they write them and they say, let me read it. In order to protect the privacy of the institutions that participate in the survey while still allowing them to do the analysis, the company that runs the survey agreed to merge in the Facebook data set into the NCHA survey and then delete all evidence of the merging, except for one dummy variable that identified whether or not that respondent was at a Facebook at that time period. So that's all they know. They merged in the data set containing the Facebook introduction dates. They add a variable to the survey listing whether or not in that semester Facebook was at their college. And then third, then they strip away any information that would have let them identify the college, including specific dates in which Facebook was introduced. That's what they're going to do. They're not going to know the college. They're not going to know when Facebook was introduced. They're just going to know that that individual at that time period was treated. Here's some basic facts. Colleges in the early Facebook groups, okay, colleges in the earlier expansion groups were more selective. We knew that. Okay, we knew that because we knew it started out at Harvard, and then it goes to Columbia, BU, Berkeley, Stanford, Yale, all that stuff. So we know that it was rolling out and it was hitting the Ivy Leagues first. Okay. So they were more likely to be, they were more selective in terms of their test scores. They were more likely to be on the East Coast. They were more likely to have undergraduate programs, residential undergrad programs than the college later, right? So some of the colleges later were commuter schools, and so these early ones were residential, more likely. So there's a lot of things to show that there was lots of differences. It wasn't random. It's not random that it's getting rolled out. And the earlier groups were selecting on wealthier students. And the earlier groups were also selecting on students who had very poor, this was very interesting, all of these people also at the baseline had worse mental health outcomes than the later kids did. So the early adopters, even though nobody's choosing, it's interesting, the choice parts here. Nobody's choosing for their school to have Facebook. They have no control over whether or not their school gets Facebook. They have control over whether or not they get on Facebook, but they do not have control as to when they can get on Facebook. They can't do it anytime. They have to wait until it rolls out to their school. When it does roll out to their school, if you look at the average mental health outcomes at baseline of everybody at T-1, if you looked at it by treatment group at T-1, the people that get Facebook first had worse baseline mental health than those later, which is interesting. All right. So there's tons of very interesting data, lots in here about mental health. That was part of the cool thing in this, is that they have so much data. They create their own combinations of questions into indices, into an index of poor mental health. The higher numbers mean worse mental health, and they're going to make it. Okay. So they're going to create an index, and then they're going to transform the index into a Z-score. And a Z-score means that when you look at a normalized variable, okay, regressed onto a dummy variable, the coefficient on the dummy variable will tell you that when this dummy variable goes from 0 to 1, the outcome changes by a coefficient, and that coefficient can be interpreted as a standard deviation. Okay. So for people that work in education, you're used to doing this stuff all the time. In psychology, you're used to doing this all the time. Outside of those fields, it's not as common, but that's what they're going to do. They're going to be able to interpret each of the coefficients as a standard deviation in the outcome, but it's going to be a standard deviation interpreted, interpreted as like a causal effect. It causes a standard deviation change in the outcome. So the treatment effect itself is like measured as a standard deviation. When I say it that way, it's a little bit harder to interpret. But anyway, so here we go. This is their two-way fixed effects. Notice the traditional robustness table. Okay. Each column adds in something else till we get to the very end with the Facebook expansion group linear time trend. Okay. 0.13 Facebook post-treatment, 0.13. And notice this also, how they label it. A lot of people label things as average treated on the treated, especially after they've had a workshop. Do not do that. Label what the treatment is. Label it, because the reader, again, don't assume that readers know what an average treat on the treated is. You're going to have to you're going to put this in normal words. You want this to be something that an intelligent person can read. Post Facebook introduction. Coefficient is a standard deviation. 0.14, so a tenth of a little bit more than a tenth of a standard deviation increase in poor mental health. Put in the controls, 0.12, but gets a little bit, but the standard error goes down, but the coefficient goes down. Put in college fixed effects, that cuts it by a lot. Goes from 0.12 to 0.08. Put in the Facebook expansion group linear time trends. So that must be some sort of like treatment group, times a linear time trend. Pulls it down a little bit, 0.07 of a standard deviation. They then, because they have such rich data, and this is again a strength of the project, is just, it's not just the experimental design part of it. It's also that they have great data. They begin to look at each of these things carefully. They group them together. So they have here like, did you feel hopeless last year? There's a big one. Did you feel overwhelmed? Not significant, but positive. Did you feel exhausted? Positive and significant. Did you feel sad? Positive and significant. Did you feel depressed? Positive and significant. Were you contemplating suicide? Did you attempt it? Those are positive, but not significant. Were you depressed? Positive, but not significant. But the overall symptoms depression, which is different than this one, that's their index of poor mental health. That's this one. That number right there, that's this, 0.077. But these break them all down. So there's a positive increase in symptoms. There's a positive increase in anxiety. But look at this. There's some interesting things here, but nothing on anorexia, nothing really on bulimia. So it's like, but usually probably these are all correlated. These kinds of things that happen to cohorts of students, it's probably highly correlated, but not here. Not here. It's just operating on specific kinds of mental health problems: anxiety, hopelessness, exhausted, sad, depressed, but last year depression, last year severely depressed. Other symptoms, anxiety, but not those kinds of anxiety. So these are the depression symptoms. These are the anxiety symptoms. It is anxiety, but it's not food related. Depression services, positive but not significant. Overall index, positive. Worsening of mental health. Then the killer. So here's part of what I think is probably got to be resonating with a lot of the readers, is that 2A fixed effects does not find anything in the event study, which is what we know. I mean, we know it is interesting that it does find something. It does find something in the static specification, but the event studies are biased down. And if you remember, like that was part of the results, is that these leads could be biased downward. Now, here you see Borasak et al. Always floating up. The Borasak et al. Results are smaller than Callaway Santana. Callaway, Santana, Sun and Abraham, the Chase Martin, they are the largest effects. They're not different from Borasak et al., but in that third wave, 0, 1, 2, 3, they're larger point estimates. All of them are different from 0, but these three are different from 2A fixed effects. This one is not different from 2A fixed effects, but this one is different from 2A fixed effects. These are. So that's one thing that's kind of very striking about this. And then Borasak et al. Is basically always 0. Callaway Santana is almost always 0. Sun and Abraham, almost, always. These two are a little bit off. The Chase Martin is, a little bit, it's a little bit larger standard errors here. It goes back further. So you've kind of got this like very striking, for anybody that's been paying attention to the diff and diff stuff, the the thing here, you would have to read this probably, it's a bit of a sensational result because it's not just saying that there's positive effects. It's also saying you wouldn't have found it with 2A fixed effects, which has probably got to be, there's like a lot of things going on with this study. This study is both getting to be like a first mover, introducing the methods into the top journals, and at the same time showing the importance of the methods too. That's the other thing that probably is going on here that's not always going to be true. And then they sort of break it down and they start looking at heterogeneity in different ways. One way they look at heterogeneity is they try to say, well, who's probably going to have a susceptibility to a mental illness? They have like a way of scoring people, and the effects are the largest for people that are more likely to be, to develop a mental illness. In fact, that's like, sometimes the only time there's any effects. So there's index on poor mental health, index on depression, indexed downstream effects. They're always finding it larger for the people most likely to have mental illness. I'm going to skip that. And then they have these effects on these downstream academic effects. Is there any academic performance ADD related things? Yes. Is there any academic performance depression, anxiety disorder stuff? Yes. Any academic performance eating disorders? A little bit, but not significant. Sleep problems, a little bit, but not significant. Performance stress, a little bit, but not significant. Overall, positive effects. Well, I think there might be some things, Sebastian. I've got a right here. I have right here code that'll do it. Event plot will do it. So I'm going to run this in the background, and my code will do like 6 of them. And so I've got this shared, makes them all. Okay. But we'll see. It'll take like a couple of minutes to do all of them. But there is packages in Stata, and I believe in R also, but we'll look at that. I know there is in Stata. I don't remember if there is in R, or I don't know if I have it in R coded up. And then they have their mechanism. They have their mechanism result. And here's their mechanism result. They only really are finding effects for people that live off campus and then people that have credit card debt. They're not finding strong effects for people that live in a fraternity or sorority, although there's some people that work, people that are overweight, but they're finding effects for certain groups of people. Okay. So that's one. That's one paper. All right. And then there's this Brynjolfsson, Danielle Lee, Lindsay Raymond paper about not ChatGPT, but it's kind of like it. So there's this unnamed firm that releases gradually a chatbot, generative AI based chatbot to 5,000 customer support agents. Okay. Now remember, under Son and Abraham, an event study will be biased if the rollout leads to treatment groups that have different treatment profiles. All right. If it does not lead to different treatment profiles, right? See right here. So this Wooldridge part is wrong. So I have to like go through and do all this again. But this Wooldridge part is wrong. I bet if I just drop the 2003 after. Okay, so I'll run it again. But in my case, the treatment effects differed by group. But if the rollout is random, then it won't. And if the rollout is random, then 2A fixed effects will not really be biased. Okay? Because it's always about differences by groups. Treatment effect heterogeneity differing by group. That's what does it. And under randomization, you never have that because randomization distributes the treatment effects equally across all the groups, right? So it's going out. That's something I want you to think about as you interpret what I'm going to show you. I forgot to put it in here. So, but I'll show it to you. So it rolls out to 5,179 customer support agents. Okay. And these chatbots are not going to answer complaints. They're going to help them. They're going to help them with their complaints. It's a very stressful job. People only reach out to these people when they're furious. Okay. It's not an RCT, so they're going to do diff and diff. Main focus is going to be measures of customer support. Agents handling calls, these are human beings. All right. And that's going to be a proxy for productivity. They're going to focus on high and low skill workers, and they're going to mainly present graphical evidence, right? They're going to present regression tables, but the event study graphs are very powerful. So here's the example of the chatbot. Hi, the visitor shows up. My name is Alex. I'm super frustrated. I've had customers calling me all day saying they can't access their information on the website, or the website isn't loading. I need it fixed ASAP. And then here's what happens. The chatbot generates different statements, and then the person can read them off or copy and paste them. Okay. Here's the rollout. They do an RCT. It's very small. All right. Then in October 2020, looks like about 5% of the firm gets onboarded. November jumps up to about 38. December, almost 60. January, 80. February, 90. March, 90 something. April, 90 something. May, almost everybody. Okay. All right, so I forgot to put this in there. That didn't fix it. Huh. I have to figure that. I don't know why the Wooldridge part's not working. I'm doing something wrong. So I'll have to look at that. Anyway, so I'll figure it out. So but I wanted to show you this. So they do this. They have all the different diffs. Now look at all the different diffs, two-way fixed effects. Plus signs, the group all together. All right, they're grouping all together and they look pretty similar. Okay. Coefficients are basically around 0. And then post-treatment, two-way fixed effects is usually pretty similar. It's usually pretty similar to the others. Okay. In the log, it's a little bit lower, but in the others, well, if that's the case, then there's two things that could be going on. One is there is no heterogeneity. It's the same for every group. So that would be one thing. Or it was random. It was random with respect to the treatment effects. Doesn't have to be random, but it could be that like they're not targeting the best, the best people first or something. It could be like, that the rollout is random with respect to the treatment effects. Could still be. Okay. But then once they did that, they only did that in the appendix. The rest of the time, they're only going to present one method. I don't know. I don't understand that either, German. I don't know why it's usually larger. I need to get an answer to that. It is the standard errors are larger, but I don't know why that method is like that. And if it, and I just need to, sit down and get some real clarity around that. But it's often the case that its standard error is larger. So here they're going to look at resolutions per hour. Then they're going to look at log resolutions per hour, and it's pretty similar. Okay. But if you put it in log, then you can do percentages. Here, it's just going to be like interpretable as with respect to the units that they're looking at. So here's the log. So in the year of treatment or the month of treatment, it's about a point. it's about a 15% increase in resolutions per hour. Then it jumps to 25. The permanent is about a 25% increase in they're doing more, they're resolving more problems per hour. They're resolving more problems per hour by spending less time on each of the people by around 10, 12%. Less time, and it's permanent. So it's like a permanent reduction of handling time of about 12% fewer units of time. And so they have more resolutions per hour, less time they're spending on each of the problems per hour. They're having more chats per hour. They're doing more back and forth with these people per hour. And nothing on resolution rate, nothing on customer satisfaction, right? Then they start looking at the heterogeneity, just very similar actually to what was done in the Facebook paper. They start looking at heterogeneity by various groups. So here they're looking at how long as a customer service agent, human, how long have they been at their job and how good are they at their job at baseline, right? So they have like basically at baseline, they get a full distribution of like how good their skill is. It's going to be, I can't remember what it is, but it's like some measure of their overall productivity. Probably, you know, a combination of customer satisfaction, complaints, and all this stuff, and how fast they are and how good they are at their job. They measure it as good at their job, time at their job. So both are different measures of skill. And they look again at resolutions per hour. For the worst people at baseline, this is like the big result. For the people that are really bad at their job, okay, you see huge improvements. About 32% more resolutions per hour. If you're the best, it doesn't help you. The best people are not helped by ChatGPT. The worst people are. Okay. Then they look at it by how long have they been there. If you've worked as a customer service agent for a long time, ChatGPT does not help you. It's not ChatGPT, but it's like it. Doesn't help you. But if you've been there a short amount of time, it does. Yeah, subsamples. Yes, that's what they're doing, Lygia. They're doing subsamples. They look at it by groups. You could interact it too, but they look at it separately by group. I think. Yeah, no, I think that's right. Did they look at it? Here at the top and at the bottom are both measures of being good and bad. And then this is how long they've been here. So this is like the really, really bad people at their job. They calculate why is that? If they calculate the standard errors based on what do you mean based on the point estimate? They calculate the standard errors using well, they use the Son and Abraham's method. They show the variance. They can calculate the variance of the Son and Abraham estimator. It's the sample, this is measuring the standard deviation in the sampling distribution of the point estimator. The components. That might be different. That I don't know about. Oh, you're so. I don't know. Then, because the estimator. So I don't know. I don't know how they have a good answer to that. Because the the standard error is regarding the estimator's distribution across, many hypothetical samples. Huh. Interesting. Oh, that's interesting. Okay, well then I trust you on it. I don't really know. All right, well let's keep that in mind then. So that's interesting. So they're gonna find their effects qualitatively are coming from really the worst workers. I don't mean that in a bad way, but I mean just like these are the people in the lowest part of the distribution of baseline skill. Average handling time falls for them. Doesn't really fall for the best workers. They do not get better. And the chats per hour, big increases in chats per hour for the lowest workers. There is a little bit of something there. Resolution rate, very large for the, now see here, it masked it. So this resolution rate wasn't there in aggregate. And part of that was because weirdly enough, you're finding really large resolutions coming from the worst workers, but then from these good workers actually slows them down. This NPS, they're finding large effects for the lowest skill group here, but actually, weirdly enough, they're finding negative effects for the highest skill group, and I don't remember why. But then they do it again by amount of time. Then they analyze the comments made by the customer, and they analyze the comments made by the agent. And the language of the customer appears to sort of become better. The types of things that they say gets better. So they use this sentiment Siebert, some English language. It's some natural language processing they're doing to get scores, I guess, of how like positive the language is, and it gets better. The customers appear satisfied, or at least they're not as angry. It calms them down and stays up about a mean of 0.1 to 0.25 for drifting back down. Here, even the agents actually show signs of being more positive, but then it drifts back down. They look at it by heterogeneity. And then there's evidence of them not having to call the managers also. Reductions in calling managers, reductions in transfers, okay, being transferred to the manager. And so sort of to summarize, they provide a lot of evidence with this diff and diff of worker productivity rising. Okay, they're really leaning a lot on this data visualization for it. And the productivity increases were highest, and then they explore all the heterogeneity. They don't lose sight, of what their paper is about. Their paper is not about showcasing or showing off that they know all the diff and diff models. Their paper is still about their study. Okay, so you can't lose sight of it. Nobody cares really out there. Nobody cares about being, impressed with econometrics. They just want you to do it correctly. And, you still have to not lose sight of the importance of the paper. Okay. So kind of to just pause there before we go on. All right. Let me just kind of conclude here. First of all, we learned that diff and diff is not a regression. It is 4 averages and 3 subtractions. It's just that a particular regression specification will calculate 4 averages and 3 subtractions. We saw that diff and diff could be used to estimate average treatment effects. You needed parallel trends, no anticipation, and SUTVA. All right. The diff and diff equation is different from the average treatment on the treated parameter. Those are not the same thing. Okay. Diff and diff calculations are attempting to get estimates of that. And they can be biased or not. Diff and diff was equal to the ATT if parallel trends was true. No anticipation, SUTVA also. It's not verifiable. So it's a difficult assumption. You don't have like all that. You can't, it could hold in one data set and not hold in another. Two people could be studying a phenomenon, two different data sets. Parallel trends could be true in one and not in another. Okay. So parallel trends is not something a model fixes. It's something a control group fixes. And some control groups will satisfy parallel trends and some won't. It's a design issue. Okay, thank you, Reese. So evidence for parallel trends comes from the pre and the post. Nobody can. Eduardo, nobody can prove parallel trends. Okay, it's not provable. It is not verifiable. Okay, so that's what you have to always remember. Parallel trends is not verifiable. Evidence for parallel trends comes from two separate things: event studies, and that comes from coefficient plots and confidence intervals to check if the pre-trends are zero. This is evidence that the two groups were trending similarly pre-treatment. You get it from the event study. You get it from the event study. This is evidence that the two groups were trending similarly pre-treatment. Okay? You need point estimates that are zero, preferably, and tight confidence intervals. That's what you're looking for as evidence on the pre-trends, and ideally on the post-period falsifications. Post-period falsifications tell you about omitted variables in the post-period. Pre-trend coefficients tell you that these two groups were trending similar. When you have both of them, you have a very powerful design because you're showing that the groups are looking pretty similar and you're finding that there doesn't appear to be some other explanation for the results. Falsifications rule out other explanations. Event study plots tell you that groups are similar pre-treatment on trends, which is what, and you're hoping that that means, therefore, they would have continued to be similar. You put both of them together, and it's very, very powerful. So those are the two things you really want. You can't, not every paper has a falsification, but every paper has event study graphs. Okay, every paper has event study graphs. So the roadmap, remember the roadmap for this, for your diff and diff? Can you show the kinds of evidence that you want to show? Fight. First order effects. Figure out what it is that would be indicative of your treatment, quote, working, meaning people getting on your treatment. Okay, that's the first thing. Try to find diverse amounts of evidence for that. Okay. Second, main results. What is your study about? That is your claims. It is not your evidence. It is your claims. Third, event study graphs. Those have got to be a big part of your paper. Okay. Keep in mind these pre-trends and these parallel trends are not the same, but the pre-trends are evidence that you might have parallel trends. Falsifications, if you can find falsifications, use them. They need to be good ones. They need to be things everybody kind of is impressed by, right? Sometimes a good falsification almost feels like its own paper, like finding no effect of Medicaid on people that are not eligible for people that stayed on Medicare can be kind of interesting to people. And then mechanisms. Can you find any explanation for why that's there? These are the 5 things that usually I see like as a good 5 things to focus on in terms of presentation. But sometimes parallel trends is not realistic. You go through all that, you just can't do diff and diff. The event studies look bad. Covariates don't fix it. Triple diff doesn't work. Your violation of pre-trends. If you only have 2 periods, then you can't do event studies. It's going to weaken it. There was a time in the mid-90s where you could get in the AER, the American Economic Review, with 2-period data. That's going to be a lot harder now because everybody's going to question it. They're going to want to see evidence for parallel trends. So all you could do with 2-period data, probably, Saban, is falsifications. But of the two, this one will be valued less than this one. That's been my opinion. You have to get very lucky. If you have a two-period data, you probably have to get pretty lucky to convince somebody of parallel trends without an event study. So if at the end of the day, you just kind of feel like, you don't think parallel, like for instance, here's a paper. We're looking at the effect of getting diagnosed with depression or reaching clinical thresholds of depression on various outcomes using Scandinavian data. And like, here's one, they meet this is Callaway Santana. They meet threshold levels. They don't know it. They don't know that they actually are depressed. They don't know they're clinically depressed. They aren't told it, but we know it. We're finding, we look at whether or not they are dependent on public resources. Okay. Well, yeah, I find some positive effects, but I mean, come on. I can draw a line right through that. That looks like a trend. That is what people are looking for. The only really good measure that we have of in this study is this thing called a sense of coherence. And we do find huge reductions once they meet clinical levels of depression. We do find like big reductions in this sense of coherence score. Okay. But people are but like, that's the thing is like for this one, it just doesn't look good. We're going to try other things. We're going to get covariates, but I told the group, I just said, I don't think anything's there. Now that's how I ended up quitting that's how I quit the Craigslist birth rates paper too, is I said, I don't think anything's there using the pre-trends, but you don't have to give up on the paper. You probably just have to give up on that estimator and go about it a different way. So diff and diff may not be the way to go about it, but you can do other things. So one other thing that we do that you can do is synthetic control. So you might need to create your own control group for which these trends hold. And that is what I'm doing in this next workshop. That's the first weekend of April. I'm doing in 2 weeks is this 2-day synthetic control workshop where people construct their own. I think probably 3 to 6 periods, 4 to 6 is what people usually are presenting. Much more than that doesn't ever seem to be, like needed. I mean, there's no real, it's very subjective, Eugen. You can definitely have too few. You probably can't have too many. And I never see more than like, I definitely see, 4 plus is pretty common. 4 plus is pretty common. And so if you really, at the end of the day, after doing a lot of evaluations, just are left feeling that I do not feel good about my comparison group. I do not feel good about my comparison group. They do not satisfy parallel trends. Remember, failing parallel trends doesn't mean you have to quit your project. Failing parallel trends means you're not going to be able to use that diff and diff estimator, assuming that you're specifying it correctly. Okay. But before we quit, I was going to show you this. I have here in the lab baker.do solutions, I've got estimators baker.do, and I've got estimators castle. dot do also. And so in estimators baker dot do, what I've got is I'm going to go through and estimate two-way fixed effects, store the results. I'm going to do that high dimensional fixed effects, store the results, use event plot to generate. I don't have to do it that way. I'm really just going to have to store these estimates here. Then I do Sun and Abraham, which can be done using event study interact. That's the command they wrote. Store it all. I'm gonna store it when I do event study interact here. I store it here. So I'm saving it for later. Callaway Santana stores, I'm gonna store it here in something. Anytime you're doing one of these overlaid plots, you got to run all these models and store them somewhere. BJS, store it. It gets a little easier for some of these. Gardner, store it. Wooldridge. Now I got to put this in a matrix. And then I plot them together. So the command to plot them together is event plot. And then I'm listing it all out here. So when you do it yourself, if you want to use this, you can do it yourself. So when we did it for our Craigslist paper, the new one, don't judge me for how bad this is. Yeah. So I do all of them. Okay. And when we do it that way, we do find now when we aggregate it to the annual level, we aggregate it to the annual level. So some of the weird things that we were finding, we don't find anymore, but we used to find it. No, it's not just in Stata, but how do I do it? So let's see, DID packages are I'll ask Kyle. How do we do it as oh, here we go. Oh, of course it's broken. So I'll ask Kyle how to get it. But I'll find it. All right. So let's take a real quick break. All right. Let's take a quick break. Let's take a 10-minute break. Let's take a 10-minute break. Come back at 07, and then we will go through the Callaway Santana paper. The code for estimating anything is still not available. So all I'm going to do is just walk you through the parameters. All right, I'm going to walk you through the parameter and help you sort of learn a little bit about this method, but we'll come back in 10 minutes. Go ahead. All right. So Kyle said, yeah, you get it in R within DI2S. And it's called, he said it's called the event study, DID2S event study. So it's probably in the vignette somewhere. Yep, here we go. does all of them. Wonder if he's got the picture. So yeah, so it's in here. There's it's in there. You can run that probably and explore this a little bit more, but I'll just put that in our chat, and there is a way to do this in R. So maybe it's like right here. Anyway, so you could probably, all right, you can figure it out. All right, so then the last thing in the Baker duty, I think. Huh. You run the whole thing and it does that? Run it all at once? Not line by line? On Son and Abraham, it's a problem with Son and Abraham? Is it only breaking it at Son and Abraham? Oh yeah, Taha, you have to change that. That was something that came up yesterday. You have to change it to this. Change that to that. If you haven't pulled the latest baker.do, it won't work. Let's see. All right, so avar. You're getting stuck at, I don't know why. MK. Let's see what happens. My avar is working. Why is that? What is avar? I do not know. Let's see. So have you reinstalled it? Maybe delete it and reinstall it. Avar. I don't know either. I don't know. That's weird because it works on my side. So, Ronnie, it works on my side. So it could be you might have hmm. Watch me just have broken it. Okay. All right. Well, it's working on mine. I don't really know why. Okay, so let's pull up the last 45 minutes. Let's go to Causal Inference 2, slides, and we're going to go to non-binary. It's 58 slides. And gonna just try to explain a little bit. I've been so we're gonna just go through this and try to understand a little bit about the continuous diff and diff situation. All right, let me let me get into it. So it's very common in panel models to use a treatment variable which is continuous and not binary. Example would be these minimum wage papers, my JHR paper on abortion clinic closures, increased travel distance, people that are studying the impact of vaccinations or vaccination rates, price elasticity of demand uses continuous prices. So all these issues about these treatment intensity.
where you think that, I believe that the treatment is not just a non-zero event, but it's like how intense people will get treated. Researchers will typically use two-way fixed effects, or they might use a count model like Poisson for that kind of thing. And those are known to be unbiased. Okay, those are known to be unbiased. So, here's two quotes from two writers. So, the two-period regression estimator can be easily modified to allow for continuous or at least non-binary treatments. That's Jeff Wooldridge. Angers Kempishki, and they're mostly harmless. A second advantage of regression, diff and diff, is that it facilitates the study of policies other than those that can be described by a dummy. Okay. So here's a bunch of quotes from Twitter back, 4 years ago, 3 years ago, when there was, I think, probably a major time when people were wanting to know more about diff and diff in general. And there was broad issue awareness about two-way fixed effects. So you got like Hani. I remember seeing a paper about estimating event state with a continuous variable. On this point, I'm very curious about how much issues you point out with diff and diff design, variance weighted of treatment effects and bias in the case of time range matter for continuous treatments. Does anybody have any reference on this? And it just goes on and on. Okay, it just goes on and on. There were all these periods where people were really had lots of questions about continuous treatment. So what we want to know is what of what we have learned is going to carry forward. All right, well, Jeremy, let's see. Let's see if that can be answered with cumulative binary treatments. We're not going to be thinking, we're going to be thinking really in terms of the idea of a dosage, treatment intensity. I'm not sure cumulative, if it's a binary treatment, if it's still a binary treatment, then everything we've done so far holds. And you might just be trying to, what is AVAR? I'll look in a minute. You might just be having to interpret the treatment parameter differently if it's accumulating. Okay, but what we're wanting to do now is figure out what of what we have learned what of what we have learned carries forward to the continuous case, or is the continuous case really and how much of the continuous case is really brand new? So some of the problems with continuous have nothing to do with differential timing. Maybe most of it doesn't have anything to do with differential timing. Okay, so we're just going to focus on the issues around the defining of the parameter, and then it's not really probably. It's probably a lot more time would be needed now that to really even get to the bottom of this one. But let's see. So first thing this is something we've already done a bunch of times. So why in the world did I cover all that? That isn't. Oh, I see. Okay, I guess I was going to show you one thing. So remember when I was showing you on that second day, we were doing all the covariates, and I was showing you that you could run this regression. I need to label that better. Here. And I was like, look, this is not a regression. This is not diff and diff, but it's a regression. And I was like, look, you have here this heterogeneous treatment effects with respect to the covariates. And, you end up with all these different treatment effect parameters. You end up with all these treatment effect parameters. You got the average treatment effect was at 2,500. That's coming from right there. But because of this heterogeneity with respect to the covariates, units with different covariates end up with different treatment effects. So, because I've got this imbalance here in the distribution of age and GPA, I'd have some people that had an average treatment effect on average of 1962 if they're in the treatment group, but then others would have a 3,000 in the non-treated group. So, I've got three different parameters. If I run a regression with all the covariates, even the covariates that are needed in the model, age squared, GPA squared, and interaction are the variables. See, they show up there too. So I have all the variables and I control for them. This isn't a diff and diff, but I control for them. I end up with a single dummy, right? And not only is it's like not really clear how to interpret it. First of all, like which of these parameters is it even trying to estimate? Okay. That one's 2,500 and that's not a 2,500 and that 2,500 is not in the confidence interval. So that's one thing. It's not a 2,500. If it's biased, if it's a 2,500, even though I have all the correct controls. And so what we did, I think we did this on Tuesday, is I said, you can use a regression. You can use a regression and you can actually with a single regression get both of those numbers, but it'll have to be calculated using a fully saturated model. And I went through and I said, you got to interact treatment with everything. When you interact treatment with everything, you then have to basically recover the right there, the 2,500 on the fully saturated, that'll be the average treatment effect. But then the average treatment on the treated, it's like you have to take each of them and then sum them together, multiplied by the mean of the covariate they're describing in the treatment group. And only then sum delta if treat, that's the average treatment on the treated. And that's what I get using that saturated regression model. So the first thing that we're just going to kind of see is that, you've got to be attentive. You've got to be on the front end, very, very specific about what your parameter is. Okay. Because if you're not very specific about what your parameter is, then you're not going to know the model to use. You're not going to know the specification to use. Okay. So we said, if our goal is to estimate the average treatment effect, I run the saturated regression model and I get it right there. That's the average treatment effect. But the average treat on the treated is not that simple. It's not that simple. You have to use all of it. Okay. You have to use it in a specific way. So where does that have to do with this? Okay. It's not as straightforward, even within this whole issue of the continuous. You've got to be really clear up front what parameter you're even trying to get. So what is the parameter that you're trying to estimate in the first place will help you articulate whether or not the how to interpret, that leads you into it, and that'll help you understand why that continuous diff and diff creates some challenges, right? Because we're going to go through here. There's some new terms that we're going to look at. There's a new causal parameter. One causal parameter that you already know is the average treatment on the treated, right? And you can think of when you're in this world of this dosage idea, okay? Average treatment on the treated parameters are pretty extreme when you're thinking about a dosage, because average treatment on the treated would mean here is my health outcome when I take this dose of Tylenol, right? I take 200 milligrams of Advil. Okay. That's 4 of the Advil pills I have. I take 200 milligrams. All right. what do you want your counterfactual to be? Is your counterfactual to not take any Advil? That would mean 0 milligrams, right? And so then you would compare the 200 milligrams with the 0. That would be like an average effect where the counterfactual is, here's what I get when I do 200 milligrams. That's my dose. And here's what I get when I don't do anything. And so it would be dosage level minus nothing. And that's like an extensive margin causal parameter, right? Everything we've been doing has been that kind of situation. And even all of our treatments had a dose. They were like, the dose concept was like, you know, do whatever this law is. You know, I could have done the law in a different way. That might be a different kind of dosage to it. I could have done it in a different way, but I did it this way. And the counterfactual is going to be never did it. We were always using these never treated groups. But what if it's not like that? What if that's not your question? What if your question is not about what is the effect of using 200 milligrams versus nothing? What if your question is, what is the effect of using 200 milligrams versus 150 milligrams? Okay. Well, that's a different causal parameter, and it's not an average. It's not the same one. It's not the same one. The dose parameters have to do with moving from one dose to another. It's an intensive margin causal parameter. Here's what I get when I take 200 milligrams. Here's what I get when I take 150. I want to know the effect of moving up in dose. Okay. So we have to spend time, and that's what we're going to do for the rest of this, is just try to understand the dose parameters. All right. So the dose parameter goes back to Angerst and Emmons, I think, 1995. And it's, we're going to express our average treat on the treated first in terms of dosages. Okay. So here's what we're going to get. We're going to get ATT AB, all right? Because it says here DD, but I want to explain what A is. A is the okay, I'll do what B is. B is which dosage group you belong to. A is which dose you chose. They don't always have to be the same thing. Sometimes they are the same thing. So it's like, I belong to a group of people who have 12 years of primary, secondary school, 4 years of college, and 5 years of graduate school. So my schooling dose is 12 plus 4 plus 5. That's 12 plus 9. That's 21 years of schooling. So that's my group. That's my group. My dosage group B is the 21 years schooling group. But I could have chosen to stop at a college degree, which is a schooling dose of 12 plus 4 or 16 years of schooling, right? So that would mean I have here ATT, years of schooling group, okay? Right? And so when you're estimating an ATT, all right, for a years of schooling group, it will literally be, I mean, it's supposed to be expectation Y21 minus Y0 for the 21 years group. Okay. That would be like what this means in this context. All right. So the average treat on the treated, which is a dosage category that compares you to some, never treated situation. the ATT of the dose for the groups that chose that dose, right? It uses as its comparison a no dose situation. All right, so here's the, I was looking at your question, MK. Here's this old Angrist and Emmons paper, two-stage least squares, estimation of average causal effects. It's one of their IV papers. Here, the variable, so like the original IV papers, they were all about the local average treatment effect paper in 94 in Econometrica is got a binary treatment and a binary instrument. And this is a paper that looks at treatment intensity. So it's a continuous treatment, but I think it's still a binary instrument. So they like analyze it. And this is what they say. They have this parameter called beta. It's continuous treatment. They're going to call it, they have to turn all these continuous treatment things. So you have to understand, like reading Angrist and Embens now that I know a little bit better, all their work together in the 90s, a lot of it was on IV, if not all of it, was on instrumental variables. But instrumental variables was part of the way in which Embens gets hooked into this potential outcomes framework. I believe that prior to Josh and prior to going to Harvard, honestly, he was not going in that direction. Embens was not working on potential outcomes. And had Embens not gone to Harvard, I don't think Angrist would have either. He did not learn potential outcomes at Princeton. He gets to Harvard, and Don Rubin is writing about on potential outcomes, and Jamie Robbins tells him to read Rubin, but they had not really clicked when they had like reached together. So Embens really is, it's like a miracle. It's all just like a perfect thing for the two of them being there. And so they end up writing all throughout the 90s, really focused on this treatment effect, like theoretical framework. And they basically go back and just like, Clement and Xavier and Kirill and Yarville and Pedro Santana and Andrew Goodman Bacon and Brant Calloway, just like they have just solely focused on diff and diff, Angrist and Embens were very focused on IV throughout the entire 90s. And so they go back and they have like a new theoretical interpretation of that continuous treatment idea that gets fleshed out a little bit later in work with Katie Grady in their fish paper. They have an empirical application of it. So they call beta the average causal response. They don't just call it beta like the way it's normally done. They've got to turn this thing into a treatment effect parameter. So they come up with this average causal response function. It's a weighted average of causal responses to a unit change in treatment for whose treatment status is affected by the instrument. It's all in this IV. It's coming up with this complier concept, but it's just going to be focused on average causal responses, right? And it looks like this. So this is for a project of mine with Manisha Shah and Amanda Nugan, where we're looking at where laws were passed in this state where they lower massage parlor fees for like requirements. Some cities lower it a lot, some lower it a little. Okay, some lower it a lot, some lower it a little. And so this is what a average causal response function is. Average causal response. It's a dose curve. It doesn't have to be curved. Okay. Remember, these treatment effect under the potential outcomes, everything under treatment effect like frameworks, the potential outcomes can be anything. So they don't have to go like this. Okay. It doesn't have to show like diminishing returns to something. Right. But I'm going to have that be like that. Okay. So what you've got is on every point of a average causal response function, all right, it's measuring the average treatment effect for the treatment group at that time period, but we've got a particular group. Okay, so this is like city A, and city A has a distribution of treatment effects. They have a distribution of treatment effects. The treatment effects go all the way from, so this city, I don't know what this city does, but this city could set its massage parlor fees to $100, or they could set it to $50. Every point on the function is measuring the ATT, and the ATT is this, okay? So if city A chose 100, then the average treatment effect for city A is that number. So this is the average causal response relates the dosage to the treatment effect. Okay. And you can have different groups. So you can have like city B and you can have city A, and they might have different response functions. Okay. Like in an RCT, everybody has the same response functions. Okay. Because an RCT is the treatment is independent of the treatment effects. So as a result, all the treatment effects are just the average treatment effects are the same for both groups. The average causal response is the same for both groups. So these kinds of issues that we're going to talk about never really show up in an RCT because sexually transmitted infections. We're looking at the effect on sexually transmitted infections. And but we've kind of like put it down because of the need to get the code, and we don't have the estimator just came out, and so we've just been sitting on it because we were using two-way fixed effects. So we're waiting. So we have this ATT here, and you've got here again interpretation issues, right? So like I have here a massage parlor fee of $100. What do I say? Thought it was a massage parlor. That's how I spell it. Massage. Oh, am I pronouncing it different than you're used to pronouncing it, Way? Oh, massage. Okay. So here $100, and for city B, the $100, that would be city B's average treatment on the treated, and then that would be city A's average treat on the treated. Notice they're different. Okay. So that's also possible. You could have people with the same dosages that have different average treatment effects. Okay. This is going to come back later, but you can have this curve here just shows that you've got different groups. They maybe are not randomly in their groups. And there might be gaps. There might be gaps between their two treatment effects. So, here, this is from the paper by Callaway, Goodman Bacon, and Santana on it. The causal parameters in a continuous diff and diff design there's two of them. Well, there's actually going to be three, but for now there's two. There is the ATT here, and there's the ACRT. So they call this the ACR. They're going to extend it. And they're going to call it the ACRT. And all that the ACRT is telling you the slope of the average causal response function. The figure plots all the ATTs. That's one way of putting it. All that the figure is plotting is all of the ATTs associated with a dose. Okay. There are two causal parameters there are causal parameters for two doses, D and D prime. Okay. There is ATT here at that dose, and then there's ATTD prime, but for the same group. So this right here is the D group, This is the group of people that take 200 milligrams of Tylenol. But, so that at 200 milligrams of Tylenol, the group of people that take 200 milligrams of Tylenol, that is their average treatment effect. If I was to give the people that take 200 milligrams of Tylenol and increase it to 250, okay, then I've got a average treatment on the treated for the 200 milligram group. I've got a average treatment effect for the 200 milligram group if they took 250 milligrams. Okay. So I've got two things I can do. I could compare here. All right. I could compare the two ATTs. All right. I could compare the two ATTs for like a multi-valued dosage that makes you jump from D to D+1. I could imagine getting a change in the ATT. And the change in the ATT would be going from one discrete number to another discrete number. It'd be like if I'm thinking of dosages in a discrete way. Versus a continuous, if it's truly continuous, I could take the derivative at that point. I could imagine just increasing D by epsilon and then just seeing, what happened. It would be for a, continuously distributed dosages, there might be an ability to take a derivative right there. Okay. Well, I can take a derivative, but that was what you would get for a continuous dose. Okay. So the ACRT is basically the tangent line. If it's continuous, and for the discrete dose, it's just connecting it. But if you step back and you think about it, if that's what you're thinking about, if you're thinking about connecting if you're trying to think about looking at the change in the dose from one non-zero number to another non-zero number, then the interpretation is, well, what was the treatment effect at this dose? What was the treatment effect at this dose? And then look at the change. Okay. So the ACRT, yes, that's what you're gonna need a lot more. So what is the ACRT? The ACRT is the causal effect of dose this versus dose something else. D, that should be a lowercase d for that group. Okay, so it's a lot. So there's a couple of things with this. First of all, the ACRT is for a given group. That's one thing. It's for a given group. Secondly, it is for a chain. It's only going to be about comparing different dosages. Okay, so you're not going to be able to say stuff over here. You're not going to be able to say stuff over here. You're just going to be getting parameters that are local to a particular group and particular dosages. You're not going to be able to make statements beyond the dose, the min and the max. Okay. So here's the definition of the ACRT. The ACRT is for the treatment group. Okay. And I'm going to imagine I've got some particular, group that's D prime. They're at D, and I'm going to allow this dosage to go up by an infinitesimally small number. And that change in the ATT is right there. That's the ACRT. Average causal response parameters for absolutely continuous treatments are defined as the derivative. It's a derivative. The ACRT is a derivative for the continuous treatment. Partial derivative ATT with respect to L, where L is the variation in the dose. Okay. ACR is the change in the derivative of the average treatment effect. And they're different. So you have like an average causal response function, which traces out all the average treatment effects. And you have an average causal response treatment set that collects all of the ATTs as they relate to the dosage. All right. Now, because we're talking about it in this way, you could have, now that we realize that this is like, all it is collecting all of the average treatment on the treated, you could have heterogeneities. You could have, at a small dose, some effect that gets larger, maybe it peaks, and at higher doses, it goes down. Why? I don't know. It doesn't really matter why, right? Atheoretical, everything in potential outcomes has no scientific theoretical baggage. There could be something like this for agriculture, but not in a behavioral science, or it could be in a behavioral science and not in the physical sciences. Who knows? Okay. It's just going to be, though, that it's possible. You have to, at least this potential outcomes framework does not allow there to be any shape. Okay. So here's why this matters. Right here, the ACRT has a positive slope. Right here, it has a negative slope. All of these treatment effects are positive. Okay. All of these treatment effects are positive. This treatment effect might be positive. This treatment effect is positive. This treatment effect is positive. That one's positive. That one's positive. That one's positive. That one's positive. But the slope is negative. Okay. And if you don't know how to interpret the parameters, you could easily see something negative and think that it is a negative treatment effect, and it's not. It's the change in the ATT from one point to another, but it's a change in the ATT where? Right there. If you were to change it there, it would be something different. So all this stuff gets very complicated. So the authors are going to lay out 5 assumptions. I'm going to focus on 4. All right. 4 assumptions. Random sampling. All right. But put that aside for now. Continuous treatments is going to be 2A. Multi-value treatments is going to be 2B. The rest of it, pretty much straightforward. No anticipation, parallel trends. All right. So estimating average treatment on the treated is straightforward. You use diff and diff. Okay. To estimate the average treatment on the treated, you use diff and diff. It's the change in Y for the treatment group minus the change in Y for the non-treated group. So this is the dosage group, and this is the no-dose group. Okay. So in order to estimate average treatment on the treated, you've got to have no-dose groups. Right. So no anticipation and parallel trends converts this simple before and after into an ATT. All right. So the ATT is using as its counterfactual the no treatment. So treatment is a dosage compared to a 0. The ACRT is 2 different ATTs. All right. Now we know how we defined the ACRT. The ACRT is a theoretical object. It's the slope of this function. It's the slope of this function with this continuous dosage. It's the slope, and with the discrete dosage, it's just a line. It's just a line connecting the 2 points. So that's the definition. That's not how we estimate it. That's a definition. So the question was, how do I estimate an average treatment on the treated? I have to do diff and diff. To do diff and diff, I have to have an untreated comparison group, no dose. So ATT, you still need SUTVA. You're going to still need no interference between the 2 groups. I just need to go back and probably always put SUTVA. This workshop has gotten so long that I've kind of got slides where I am lazy about it, but SUTVA, you need SUTVA. You always need SUTVA. You always need SUTVA. There cannot be any interference between it. When you don't have SUTVA, you usually have to introduce new assumptions. But SUDFA has to do with the two groups. So we're going to have, when this group gets dosed, this group does not get dosed. Okay. So as a result of this group not getting dosed, both of its realized outcomes are Y0. And because of no anticipation, its baseline is untreated. Okay. Change in Y. So it's used. So this is using as its counterfactual the no treatment, going from no treatment to a dosage using no dosage groups. You can get the ATT. A lot of data sets don't have that though. Okay. Which automatically is going to kind of mean that what we're going to be doing might be a little bit different. So identifying the ACRT is going to require comparing two different groups of people. All right, this is where we're going to be going with this. The defining of the parameter is the derivative. The identifying of the parameter is about using different groups. So we're going to be looking at the ATTs for two different groups. All right. We're going to be using the ATT that we find for one group, and we're going to be using the ATT that we find for another group. Okay. We're building towards our estimation. Here's group A that has chosen dose A, and here's treatment group dose B that has chosen dose B. And we've got, theoretically, we've got an ATT for them. We've got an ATT for them, right? So any kind of estimation that you're going to be doing has to move through this step. So we're going to go here. We're going to go ATT BB. That's going to be this. ATT AA. That's going to be this. Okay. So notice when we do that, because both of them have a D equals 0 comparison group. We don't have differential timing in this situation, so we have this. This just gets canceled out. So the change in the ACRT, to identify this ACRT with these same comparison groups at the same point in time, those terms cancel out, and you're left with just the inside of the diff and diffs, the change in Y for the treatment group, the change in Y for the other treatment group. And it's going to be about comparing high and low dose groups. So the change in ATT, it's going to be about the change in Y for the treatment group minus the change in Y for the other treatment group. All right. So let's put it into this framework here. I'm going to slow down for a second. So here I have, this right here. We'll say this is like, DJ. Let's say that this is people who take 200 milligrams Advil, and DJ minus 1 is going to be people who take, they're going to be people who take a lower dose. We'll say 100 milligrams Advil. All right. So this right here is the ATT for our 200 milligram group. And this is going to be our ATT for our 100 milligram group. Okay. Now what I'm going to do is I'm going to add in this line right here, I'm adding in a 0. A counterfactual 0. It's coming in right here. Okay. So this part is there. Okay. And then this part is there. So that all I did was I added in a 0. I added in a 0. ATT for the 200 milligram group, had they chosen 100 milligrams, right? So that's what this is right here. This is a counterfactual, right? This is a counterfactual. What would be the treatment effect for the people that take 200 milligrams of Advil had they taken 100 milligrams of Advil? Okay. Well, now look what I have for this group right here, DJ, that's the 200 milligram people. Now I've got ATT at 200 milligrams minus ATT at 100, and that is an ACRT. The reason why that's an ACRT is look back. That's what ACRTs are. ACRTs are for a given group D, vary the dosage. That is the ACRT. And so we just now put that in. Okay. So that right there is this one plus this. Okay. Plus this right here. So we're seeing now that whenever we compare the ACRTs between two different groups altogether, we compare the ATTs for two groups. Inside that comparison is the change in the effect of the dose on a given group, the ACRT, plus bias. And to Sabin's point, Sabin said, are we going to have to assume more parallel trends? See, both of these are assuming parallel trends. ATTs already have parallel trends in them. So this ability to make comparisons already has built into it. You could get two ATTs for two groups, but if you compare them to one another, that won't get you the ACRT, because the ACRT is about a single group. So whenever you compare two ATTs to one another, you get the effect of increasing the dose plus selection bias. And what this is what is the effect here? So this is for the 200 milligram group. What is the effect had they chosen 100? Here's the 100 milligram group. Here's their effect if they chose 100. If these are not the same, then whenever you make comparisons between two different groups, like if we make comparisons between any two groups, ATTs, in order to try to get a measure of the returns to higher dosages, you always have this selection bias. Anytime you make comparison between two groups, you always have selection bias. You have to assume it away in some way. Parallel trends assumes it away, but we got parallel trends here because we're comparing parameters. So this right here, right? That is an ACRT. But if we are comparing this right here, that number, with this number right here, that number, all right? That's that. And that is not an ACT. That is not an AC. That does not measure the returns to a higher dose. That's just, but it does contain it. It's got two parts. There you see the selection bias, and there you see the causal parameter. Okay? So the only way that you can go about doing things in a continuous treatment setup is somehow you're going to have to deal with this fact that these two groups might have different treatment effects at the same dosage. And that's already kind of built into you doing any kind of estimation. All right. So under assumptions 1 to 4 here, okay, causal response parameters cannot be identified, because what you're going to get under 2A, that 2A is the continuous, and then 2B is the multi-valued. Here you have under 2A, this right here is a change in Y0, change in Y for the two groups. That's going to be a change in ATT. Okay. That's going to give you the ACRT plus the differences in the ATTs for those two groups, which means that if I am calculating, comparing these two ATTs to one another, I'm going to have the ACRT, which is this. So that's this number right here. I'm going to get the ACRT plus this selection bias. And so what we're basically saying is that parallel trends is not enough to get an estimate of the effect of the higher dose going from one dose to another. Parallel trends is not enough. No anticipation is not enough. So what do we have to assume? So under 2A, we have selection bias. And under 2B, we have selection bias. Okay. All right. So interpreting this, if you have this unrestricted heterogeneous treatment effects, you allow them to be anything. They can be different across dose levels. They can be different across units. Okay. That is itself not the problem. Randomized dosages will make it so that everybody is on the same average causal response function. Okay. Where you have problems is if people are sorting into their dosages such that, you end up with average treatment effects by dose. That's where you're going to have problems. You're going to have to make additional assumptions. So there is no, so when estimating treatment effects using continuous diff and diff, you're going to need to make two additional assumptions. One is what's called strong parallel trends. And strong parallel trends means that the change in Y0 is the same for the entire sample. Okay. It makes a very strong statement about the treatment effects. It basically means that you're going to have to, when you assume strong parallel trends, you are assuming that away. You're just assuming that all of the groups, had they chosen the same dosage, would have had the same treatment effects. Okay. So parallel trends plus homogeneous treatment effect functions. You're having to basically assume it away. So Roy model, like sorting on gains, is probably going to violate it, but not all continuous dosages might violate it. So, you might imagine that people that get the higher levels of schooling have different treatment effects. If they had stopped at college, then those people that stopped at college might be lower than those people that stopped at college, might be higher. Who knows? But they might not be the same. Okay. Whereas, so the more that you can think of your continuous doses as well, it's a long paper. But I can point you to it, Eduardo. I can show you a Substack I did on it. But it's not as no, there's somebody asked me that on my Substack. This is such brand new area. Mapping all of these diff and diffs, to be honest, mapping all of these diff and diffs into explicit potential outcomes and then beginning to explore all of their, particulars. It's kind of like, there's a lot to do. And so triple differences with continuous doses, I've not seen anybody do it. And there's going to be lots of issues with it. And it's its own wild animal. So here's what strong parallel trends means. We discussed an alternative, but typically stronger assumption, which we call strong parallel trends, says that the path of outcomes for lower dose units must reflect how the higher dose units' outcomes would have changed had they been at the lower dose. Strong parallel trends restricts treatment effect heterogeneity, and it justifies comparing the groups to one another. Absent that, comparisons across dose groups include causal response, but are contaminated by an additional term involving possibly different treatment effects of the same dose, and they refer to that as selection bias. So strong parallel trends is saying that if you go from Y0 at baseline to this dose, that it's the same for had everybody done it. Randomized dosages guarantees everybody's, I've said that. So now we're just going to real quick interpret the two-way fixed effects results. Okay, we're just going to interpret them real quick. So let's say that we ran this regression. I got year dummies, I got panel dummies, and then I've got a host dummy interacted with a continuous dose. All right, but that just means that I've got this after the treatment, I've got the treatment group and the treatment group's post-treatment dose is going to be, this variable right here, treatment intensity. How do I interpret beta? Okay, so I wanted to show you this right here. So our impression is that empirical researchers typically interpret beta right here, okay, in three main ways across papers. First, they'll directly interpret it. They'll say beta is a causal response parameter. All right, causal response parameter. And this causal response parameter will be how much the outcome is causally changing on average when the treatment increases by 1 unit. Okay. So this is the causal version that you'll get in an econometrics class. Second, it's common to pick a representative value of D and then report some, basically take the coefficient and then multiply it by some particular value. So like Daron Acemoglu and Amy Finkelstein have a 2008 paper, and that's their interpretation. Given that the average hospital has a 38% Medicare share prior to this event, this estimate, and they have a beta of 1.129, suggests that in its first 3 years, the introduction was associated with an increase in the depreciation share of about 0.42. And they say, take this, multiply it by 0.38 because because I'm going to use the baseline, treatment intensity, and I'm going to multiply it by beta. All right. And then they'll sort of report this. Okay. And then third, they'll take two different values. They'll say, all right, take 1 and take 2, might be going from the 25th to the 75th, and then interpret that as the average causal response of going from it. So there's like, either people will interpret it directly as a causal parameter, or they'll plug in certain numbers about the treatment intensity, and then they'll do it like that. Like I probably would have used a standard deviation in the treatment intensity and then multiplied the standard deviation by that two-way fixed effects. I do that kind of stuff all the time. So there's like different kinds of things people might do. Okay. So what they do in the paper, and then this is where we got to stop. So what we do in the paper, because there still is no estimator that's like circulating. So I'm still been waiting to kind of get that done, but it's allegedly coming here. So under assumptions 1A, 1, 2A, 3, and 4, okay, two-way fixed effects will be a weighted average over the average causal response function plus the selection bias plus this baseline ACR when you're at the baseline. Two-way fixed effects ends up being a little bit challenging to interpret. Using their framework, it's hard to interpret it because you've got these weights over the ACRT plus this weight here of the original ATT. And so they say here, the decompositions in the main text integrate over all possible doses, low to high. So they have here causal response decomposition. If you interpret it directly, it will have selection bias in it. If you do those levels, it won't. If you're going from one ATT to another, it won't have it. So when you do the scaled 2x2 decomposition, which is this is a scaled 2x2 going from one dose to another. Hold on, sorry. Suddenly something doesn't seem right. Okay, yeah. So if you assume so without assuming that without assuming this, that everybody's ATT would be the same at the same point, you can't get anywhere. You're going to have to make some assumption about the appropriateness of using these other comparison groups. And that's kind of assuming a kind of constant treatment effects. So here, beta directly, where it's just the direct coefficient, will be biased. If you assume strong parallel trends, that goes away, but it's still going to be this. Well, I would, yes, that's what I would keep working on it. I would write Brant Calloway and ask him, when the estimator will be available. You could try to do it yourself. They have this other way that they're going to be doing some of this estimation itself that doesn't get into the some of the weird things with two-way fixed effects. Now, the thing is, Hone, though, if you do use two-way fixed effects, or if you don't use two-way fixed effects, you're still going to have to make the assumptions about strong parallel trends. If you make the assumptions of strong parallel trends, that will go away. Even with two-way fixed effects, it'll go away. Two-way fixed effects, that'll go away if you have strong parallel trends. It's the weird weighting that can be a little bit challenging. So I might still do the two-way fixed effects and get that done correctly. Yes, I would still do it correctly. And probably if I were you, I would probably invoke the strong parallel trends and think really carefully. You're going to have to be really clear to yourself that do you think that's believable? There is no test for it. There's no test for it. You can know average treatment on the treated. See, you can know these. These you can estimate. You can estimate ATTs. You can't know ATTs for a group had that group been at a different level, chosen a different dosage, unless you have that. See, but that's extremely counterfactual. Though you don't have that. So you're going to have to invoke strong parallel trends just to get this in the first place. You can get it with two-way fixed effects. Okay, you can get it with two-way fixed effects. The thing that two-way fixed effects does is these comparative dose parameters. You'll be fine. All of the two-way fixed effects weights are not zero or not negative. That's not negative and that's not negative. It's just that if you interpret it directly here, they're like these variance weights. So you could do it. You could absolutely do it. They'd be a little bit challenging to interpret. They've got these positive weights. So you'll be fine if you know how to interpret it. So you could probably still do it. It's just that you'll have these kind of variance weights based on it. Okay. So right now, we're 10 minutes over. And I don't have, still have this all worked up, but it's probably a full day just to do continuous treatment. I just wanted to emphasize the basic principles, which is define your parameter, figure out the assumptions. If you're gonna use a continuous treatment, you're gonna have to interpret it and use two-way fixed effects. You're just gonna have to review what this means and just go through and be sure that you know how to articulate what you are interpreting. It's going to be some kind of variance weighted average over the ACRT and the ATT at this low point. And under selection bias, without strong parallel trends, it'll be biased. So you'll have to assume it away. All those strong parallel trends, though, will remove the selection bias. The weights of two-way fixed effects do get very hard to interpret. It's very hard to interpret it as a causal. Now, without simulations, I don't know exactly how bad it can be. So this is still something that I'm working on, but it will not necessarily, you want to know exactly how to interpret it. Okay. And I want to stop there and just kind of conclude here with a conclusion. This kind of conclude. Okay. So of this workshop, we've had all these basic principles. Diff and diff is a calculation, average tree on the treated, concept of the parallel trends, the falsification, the event study. Those were like our basic principles. Then we brought in these covariates, addressed that problem as a way of addressing parallel trends. Then we looked at differential timing. We looked at most of these. And then we looked at continuous treatment, at least in terms of like defining the parameters. Okay. You're going to write a paper using diff and diff at least once in your life, probably more. If you're in the workshop, it's because you believe it's important. You're going to read a lot of papers that use diff and diff. You're going to referee a lot of papers that use diff and diff. You're going to advise students that use diff and diff. There's no way going forward that you can avoid having to learn this material. So it's in your best interest to make the fixed cost investment in the new econometrics of diff and diff, because these old methods are not always harmless, right? Some of them are probably harmful, sometimes very harmful. Good news is that most of it is now available in code in all the languages. The solutions tend to have common features, so you don't have to make nearly as many choices as it might feel. The overall presentations aren't all that different. Event studies, falsifications, exploring mechanisms, heterogeneity, all those things. It's still going to be the same papers that you're writing, okay? But how you go about it, that part is outside of the workshop. Not all of this stuff but some of this stuff is still cutting edge. So a lot of the continuous is cutting edge. None of the papers have yet been published, I think, except for this one paper that just came out in Review of Economics and Statistics by Chase Martin and Hopeful. So that stuff is brand new. So the simple 2x2, okay, the simple 2x2 has its own problems when using two-way fixed effects if you include covariates, but you can address it. You either make the stronger assumptions needed to include the covariates, or you use a different estimator that does not require the same assumptions. Main problem in differential timing is heterogeneity. That's the problem. And how that heterogeneity is distributed across the groups, right? The use of already treated units is what's harming you in those studies. So differential timing, if you're not willing to make prior theories about those about those heterogeneities, then don't use two-way fixed effects. It's biased. It doesn't satisfy a no sign flip property. The weights are negative, et cetera, et cetera. So the robust diff and diff methods, they do not have any restrictions about treatment effect heterogeneity. So you don't have to worry, they do have a no sign flip property. There are no negative weights on these other methods, okay? So when you lose parallel trends, you're more than likely, you're just going to have to abandon the diff and diff project, but not the project. You're going to have to go in a different direction. And there are solutions. One solution that you're probably going to want to look into is the synthetic control methods. The synthetic control methods are all imputation methodologies like Borisov et al. And like Gardner. They just don't use parallel trends. All right. So there's plenty of them. All right. And even when the core synthetic control method fails, there's new synthetic control methods that are for failing those situations. And the synthetic control methods have now rolled out to where they're used for when you have one treatment group or many or staggered. Okay. So that, I apologize, we went over 18 minutes. I want to thank you for coming to the workshop. I hope that this was helpful. It'll take me several hours to get the recordings up, okay? And but I will just say real quick, Eduardo, if you want to shoot me an email, I can send you the fuzzy diff and diff Substack. Okay. If you'll shoot me an email at my Gmail, or you can do it at causal inf at mixtape.consulting. If you do that here, send your email there, Eduardo. I will send you the fuzzy Substack that is an explainer of it, and that might be helpful. Okay, good. I apologize. I know that I go really slow, but thank you so much for coming to the workshop, and I'll post this up as soon as possible. Okay, bye everybody.
Thank you.
All right, see ya.